Good morning, everyone. Hello. Welcome to Michael Weinstock, Director of EmTech, and I welcome you to EmTech MSc final jury. We have 7 teams, a mixture of MSc and MArch teams, and some teams only MArch members as well. And our teams have been working on their dissertation projects for the past year. And our MSc teams are going to submit their final documentation in 2 weeks' time. We have a very nice list of jury members today. We would like to welcome them. We have Andrei Martin from PLP. He's the director at PLP. Irene Gallou, the head of SMG at Foster & Partners. We have Eduardo Rico, who will join us shortly. He is the director of AA Landscape and Urbanism program. We have Axel Koerner, who is doing currently his PhD at ITKE. We have Antiope Kolonaki from EmTech, and she will be teaching with us this year. Alican Sungur, again, EmTech graduate, who will be teaching with us this year. Manya van de Worp, and also Dr. George Ioannidis are with us today. Perhaps if our jury members could briefly introduce themselves, be great.
Hello. Thank you for the invitation. It's really, I know a lot about the work here, kind of vicariously through the people that we hire, and also through just in general through the presence of EmTech. It's an institution, and I'm incredibly honored to be here and to see your work firsthand. In addition to being a partner at PLP, I also teach a design studio at Westminster, and our interests overlap in that I have a huge degree of interest in digital design, in how it's applied, perhaps outside of the traditional remit of digital discourse. So, it's great to be back into the foundation of this and to see where it all starts from. So I'm really looking forward to see your work.
Thank you very much for inviting me as well. I work at Foster's. I head the specialist modeling group, and my passion is performance-driven design. I studied here, so I'm very happy to be back. More than 10 years ago, I studied energy and environment, like building physics. And now with the work I'm doing, I'm combining the physics, the performance, and design, like from finding studies, that type of stuff. And so I'm super happy to be here and see your work.
Thank you. Hello. Thank you as well for the invitation. I studied EmTech and finished in 2013, so it's nice to be back and see how this program developed during the last years. And as mentioned, now I'm doing my PhD in Stuttgart at ITKE, and my work is related mainly to compliant mechanisms with fiber composites and biomimetics, so bio-inspired kinetic structures is the overall topic. And yeah, I'm looking forward. I mean, this looks already quite interesting and related to my work. So I'm looking forward to see what you're doing.
Hi, I'm Antiope Kolonaki. I'm an ex-EmTech student, and I'm doing a PhD in Bath. I was teaching at the AA, and I'll be in EmTech next year. And the topic of my research is layout optimization of space frame structures with a modular approach, and I'm looking forward. And thank you for the invitation.
Hello, I'm Alican Sungur. I've just graduated, so I don't have a really cool research topic ongoing. I'm 2016 graduate, and since then I've been teaching in Diploma 8 and occasionally in Oxford Brookes. And at the moment I'm working at Pattern Design as an architectural designer, and I'll be teaching in EmTech as mostly involved in computational topics. So thanks for the invitation.
Thank you. So we will start with our first team. Just as a reminder, every team 15 minutes maximum, right? Okay.
So, hello, my name is Claudio. My name is Carlos Palomera.
And I'm Itamar Amrani. We'd like to thank the Architectural Association for hosting the presentations and our visitors for joining us today. For our project, Performative Synergy, we'd like to start out with a short video.
The Category 5 storm is headed west towards Florida.
To Hurricane Irma, we've heard this already, it could be the costliest, but also the most damaging in U.S. history.
We are dealing with this hurricane that is unprecedented in a lot of areas, and even if it gets downgraded to a Category 4, it's still...
Of the two major threats during a hurricane, we'd aim to assess the high destructive wind forces of such.
Our project focuses on a bistable skin system which possesses structural capabilities and environmental benefits. This system has been developed as a material system to encompass wind forces of Category 3 and 4 hurricanes.
Within our research domain, we studied hurricanes as natural phenomena and their effects on mid-rise buildings. This induces heavy-duty workloads on like the built-in environment and design technology solutions by 2 to 5 times a year. Yet later events has demonstrated that this pace is increasing. Within a structural design, this induces high performance standards, and namely in limit state design, we observe the building structure works below its possibilities for most of the time. So we ask ourselves, like, what if an agile skill system can respond to different environmental scenario and to effectively transmit hierarchical performances?
In order to develop a bistable system that responds to this phenomena without the restriction of a single unit, rather a continuous surface, we have studied auxetic logics. Through biogeometrical examination, we understand the possibilities of expansion for this surface. Here we evaluate the in-plane expansion by examining the difference in x and y direction, associated ratios that are related with these geometries. Either each of these units is put together by a hinge or by an elastic continuous curve. This leads to the layering of two units, and the benefits include a rigid surface that when it's put together, and it will store energy and it will provide a different change in configurations.
So we started questioning about how to relate materials to such performances, either physical or geometrical. So by evaluating carbon fiber, fiberglass, aramid fabrics, mild steel, plywood, and so on, we looked for rigidity and lightness for our rigid rotating components, as well as elasticity and strength for our continuous elements, namely leaf springs. And by conducting some tests, so we apply some weight and understanding the extension of the material, we extract the material properties out of it. This was done for the purpose of creating a digital simulation calibrated to the actual physical bespoke components.
So the development of a physical model was done through material assembly of rigid and elastic layers. To connect such materials, joinery is developed based on the necessary degrees of freedom for fixed or rotating elements. Joinery tolerances are closely defined for complex component interactions. To achieve stability at an expanded state, a spring locking mechanism was devised at each connection point where the two layers are joined. This is activated at a determined angle of rotation between rigid and elastic layers. Structural analysis was done of the material component to assess material performance, specifically utilization, between the expanded and retracted states. An assembly process of a physical model for exploration of the system's out-of-plane expansion was undertaken. Pultruded carbon fiber tubing and rods were fashioned along with bespoke layers of fiberglass springs. 7 components were determined necessary to test the locations of fixed and actuating point relationships.
So several out-of-plane experiments has been run with the aim to understand the degree of expansions. We tested 2 main aspects. Firstly, the element's distance of travel against the initial surface area, and moreover, the relative rotation of the rigid elements and the leaf springs to understand the locking possibilities of the skin system. So by creating a digital model, we evaluated the potential expansion, and we questioned about architectural implications. Such a model has been calibrated for reliability against the physical one, which is this one. We call him Francesca. And furthermore, we assessed the reliability of the data. So we evaluated also the locking possibility by understanding how support points and actuator points affects the rotation of this system. And so we understood if we need to free it up or not.
From this understanding of the system's performance, we can really begin to evaluate its architectural potential. Further investigations consist of the skin's support points at 2 different states and integration of the system's agility for its potential to activate various structural elements. Spatially, we can begin to evaluate potential change in planar and volumetric spaces for opportune reconfigurability and unique experiential qualities, which subsequently could lead to improve environmental performances of natural internal ventilation and thermal comfort levels.
We perform a regional wind test of the area to find a design solution that can be suitable to provide the initial form for our architectural proposal. The result yield a high wind of 200 kilometers per hour and a low wind of 60 kilometers, which allows for a system that can provide 2 different states, retracted and expanded. This also can benefit the program as the temperatures will vary in between these 2 different states. Due to the high prevalence in the area of hospitality, we have selected this as our building type in a 15-story tower. We laid out a relationship between the architectural system development of structural performance and the skin. This will be driven by different programmatic design solutions.
So in order to understand this relationship a bit further, certain factors are evaluated which determine the skin's integration. Specifically, programmatic dimensions and functionality are directly connected to spatial opportunities, and when criticized, determine the skin's expansion area, configuration, and connection points.
So in order to propose our structural strategy for the mid-rise tower, which is a building test, we evaluate different structural strategies for high-rise buildings. So from these, we took the one that demonstrate suitability for our architectural ambition, as well as skin integration.
So to demonstrate the more frequent expanded state within the proposed building system, here we expand on the various layers. A build-up from the core and the truss system to the tendons, which support the slabs in tension, to the skin's connection points to the structure, elastic springs to the rigid units and the panelization. This exhibits a stable position within the system's bistable performance.
So we evaluated the structural performances of the skin within the two different environmental scenarios. In order to allow our system to work, we required three different components of structural integration between the two, which are namely support points, provisional support points, and actuators. In the retracted state, we see that, and we observe that, by introducing provisional support points, the load paths changes. And so the material utilization increase proportionally not that much if compared with the increase of loads. Then this has an implication over the structure, and it makes evidence of how the core is differently activating in its components between the two states.
Through the evaluation of these skin fix and actuation points, we can begin to see how the opportunity of space can arise. Here we can have an adjustable floor layout that can be executed through the expanded state. Additionally, we can see how the actuation points provide this opportunity to start the reconfiguration of these spaces.
So we continue to run further environmental analysis on the internal airflow through the system between the two states. Although, to fully understand the benefits or potential benefits within the system between the two states, further analysis needs to be done to really understand potential benefits of what might occur. Furthermore, environmental analysis would like to be done of the thermal comfort levels and the change of such, and what would be the aim to improve during an expanded state. Spatially, we'd like to continue to explore various architectural sectors and the programmatic layouts and how the skin might benefit such architectural implications, along with the approach and exploration of retrofitting the system to currently existing structures.
Yeah, moreover, the system gives the opportunity to further exploration in its logic, as well as so this led us to an initial exploration that we haven't included because it's a very early stage about folding or really elastic steel strong materials. Moreover, the scalability of the overall component within the geometry of the surface and its definition. Moreover, we can also test different multi-state positions, or also the control over the expanded geometry by a different configuration by non-uniform stiffness throughout the springs, because these are uniform. So when the actuators comes out, this follows. And moreover, for the design technology, we can explore like different materials such as aluminum frame for having like more affordable solution, or mono body carbon fiber, like as bicycles are made, for instance, and so on.
I would have some, I mean, you addressed my first question right at the end, so because you're introducing it as a building skin, but right now it's not, I mean, it's not a skin, right? I mean, it's moving triangles, but so okay, you addressed it, but how do you, so either with folding or stretchable material, but if you find the stretchable material, then let me know, because I would be very interested to. Yeah.
Well, we did, like you said, we initiated the research. We started thinking that if there's something that we can mostly PVC coated materials, lasting materials like this. But we don't want just to say, okay, we're going to use this material, we want to have some kind of
because then two of my students in Stuttgart right now develop something similar with folding, and they have basically compliant hinges. So they don't use those springs, but the energy distribution and how to get the whole system compliant is because the faces can bend and the hinges store the energy to fold back in the.
Also, there's a displacement from the initial position to the final position, from retracted to expanded.
Yeah.
So the material also has to account for that expansion. Even if you're doing one single fold, for instance, cannot be applied for that. So we were testing double folding and also dividing the geometry into three pieces, which is the triangles. These triangles, and then the middle part can be something that is like a membrane that folds into itself. And then, so there's, I think, for us, 3 different parameters that need to be accounted into this folding geometry.
But then, I mean, that would then lead to my next suggestion or question that right now you proposed it as this building skin for extreme environments, but maybe a better solution is the second layer in front of a facade system for several purposes, with maybe bending active or compliant shading devices, because there we always have the problem that things get longer or shorter, and your system could solve those issues. I mean, we did a workshop in Tehran last year where we developed a system exactly with this focus on how to compensate this shortage or shortening effect of edges in bending strips. And what do you mean with bistable? So that's my last question. Yeah, because I saw it, I mean, it's stable in all positions. It has a gradual change and not a bistable.
Achieves the fly stability between an expanded and retracted state.
But it's stable in between as well, right?
Yeah, so what we've developed currently has 2 stable states when it's locked in an open and expanded state, and then it's closed, but further exploration for multi-stable positions between the furthest expanded state and the closed state for spatial reconfigurability.
The initial, there's a sequence of events that need to happen in order to perform in bistable in both cases. So initially it starts as an open state. That way the springs, when they're put into expansion, they can store the energy. So when you release the system, you can actually unfold on its own. So you have to spend more energy to close it than only to activate it. So that's what we decided to keep on the state, because it's also.
Thank you.
Very nice presentation. I have one question. You're using ETFE as an infill. Did I read it correctly in your presentation? I have the feeling that that's the weakest component in your system, because ETFE is very fragile. So when you need to, and things in a hurricane fly around, which means they can easily damage your skin. One possible way forward is to say that divide the functions. You're trying to do, I think, way too much with one skin. And this wrapper can actually be like the filter. When you have high winds, what you want is to reduce them. You don't want to stop them completely. That's too much, resistance. What you want is to stop them, buffer them a bit. So if that system in a closed position, act as a filter, to reduce the wind, whatever is behind, the glass, the balcony, so things that don't fly around, that will be a success for me. When it's open, when the weather is nice, usually very sunny, that can act as a shading device and brings lots of nice double light in. And another comment I have to make is on the materials. I think aluminum or carbon fiber is a bit, I've seen them before. I would like you to also explore new materials, all materials used in a new ways, like basalt. You will be surprised at basalt fibers. They exist. They're super cheap and very, very strong if you find a nice way to weave them. And that's another potential material that is not as expensive as aluminum, or even more expensive like a carbon fiber. Super strong, can fire resistant, you name it. So that's like an effective buffer for these extreme climatic conditions. But again, congratulations, nice work.
Yes, I agree. I think as a system, I think that the behavior of the system is very well explained, and it's quite clear how it works. I think, as always, and I kind of agree with Axel, I think sometimes it'd probably be good to kind of be careful about overclaiming the performance. So in a way, I think the idea of this sort of being perhaps relegated as an external shading device could be more true to your ambition. But it also, I think, could be a fruitful way to sort of look at other means of performance, if that's the case. So for instance, wind, one can be more subtle about wind. So for instance, systems like this on the facade generate whistling. You know, wind moves through and then the noise becomes an issue. So then is there a way to sort of optimize it for that, for instance? So it's a much smaller claim, but it's really super important when you deal with kind of a skin. The other thing that I think perhaps I would be very curious to know more about is how the actuator interfaces back to the building itself. And in a way, kind of how is that spatial expansion sort of realized? You know, is that again, and that's another claim I think on the boundary of plausibility at now. But I think it could be a way for you to sort of kind of perhaps explore a bit more.
Really nice presentation. Also, great model, especially that one-to-one. And I think it's a really comprehensive study. But what I would like to add is, first of all, when you're explaining the potential of the shape and the system, especially potential of the system, you can introduce different shapes to prove that how flexible your system is. That can be a study. But more importantly, I think most of your studies are done in large scale in your digital model. For, as you said in the conclusion, for more detailed analysis like daylight, performance, and analyzing wind loads, you might like to work on a typical floor. So you have a middle scale between that large scale and your physical studies.
Hi. Thank you for the presentation. It was very well presented and clear. And I think I want to continue to what Alijan just said about the medium scale, because in the beginning you showed experiments you made in the module scale and how much, for example, if I rotate 1 point, how far away does the effect of this rotation go, etc. So after that, and before you go to the skin of a building scale, I'd like to see maybe a floor scale or 2 floors. I don't know. That's up to you to choose. Because you mentioned that in the actual building you have support points, potential support points, and actuators. So how do you map them out on that surface? If you choose, the scale of this is another question, but if you choose, for example, that you have a grid of where your points are, how do you pick which ones are the support ones, which ones can be potential support ones, which ones are the actuators, and how does this translate into actual space? For example, if I put it here, I gain that many meters of extra floor area.
This is like a trade-off between the limitation of the system and our architectural ambition. So why we are putting an actuation here and a possible expansion related to what's behind that.
Yeah.
And then, but then this is purely the architectural ambition. But then by doing some experiments, we said, okay, if we have a lot of actuator points, these can give more stability on the overall shape, but also the rotation of the elements is not freed up. So the elements rely on the flexibility of the springs and not on the actual rotation of the whole system. So this allows for the system to not lock. So it's between having the right amount of points and what we want to do with that.
The location of the support points, provisional. Functionality of how it might take advantage of the change in space or even configurable space. So the mapping to those locations could be driven through different architectural sectors
Yeah.
Layouts of spaces that actually can take advantage of this expanded area most of the time and then retract it versus those that might be equivalent.
Yeah, I agree that it will be good to expand on the documentation, to expand more on the architectural implications of how the reconfiguration reflects back on the space, on the spatial experience. Maybe one last question that I have: the large-scale model, the prototype, let's call it, does it move or? Can you show?
We have a disclaimer.
Okay. Let's have a look at that and we can wrap it up afterwards. Okay. Okay.
Yeah, exactly. The expansion travel length is not enough for seeing something, and also the rigidity needs to be really calibrated.
Okay. Oof. All right, thank you. Thank you, guys.
Hello, everyone. Hi. My name is Theophano, and my colleagues are Gili and Sarah, and today we'll be speaking about Sahara Sound and desert arid settlements. Sorry. Okay. So, the ambition of this dissertation is to develop a material system and a robotic fabrication system localizing. Can you hear me? I don't know. Okay. Localizing locally resourced Saharan sand. The purpose of this is to develop an iterative design process between environmental parameters, dynamic parameters of flooding, material system parameters, and a 4 design scale process in our project, so that we can synthesize all the parameters in one system, basically. Gili, you wanna?
Okay. There we go. So we began our research studying the parameters of Sahara sand. Unlike the usual aggregant used in concrete, Sahara sand is finely grinded. Its grains are small, rounded, and are harder to bind together. So our next mission was to find a suitable binder to have a composite that would work much like concrete and allow our buildings. We looked into sulfur, and we realized that sulfur has a very interesting material process. When turned at its first base, it's in powder form, but when heated to 115 degrees Celsius, it becomes liquid. And once cured, and it cures very fastly, after 5 minutes, it could bind those grains together into a very solid composite. So we tested this composite to create a material timeline to know how much time we have in order to create either extrusion or casting. We came to realize that this process is very rapid. To adjust the sand, to extract all liquids from it, at first we need to preheat it. We heat separately sulfur, and then we mix the two together. And once casting it, it solidifies so rapidly, we need to figure out a kind of process that would involve casting mainly and forward. We started testing our material for tension, compression, Young's modulus, extracted data from previous research, and also studied the effect of extra heating the material once solidifies. We came to realize that if we heat it again to around 120 or up, it starts dissolving. So in order to find a proper binder for the future components that will be designed, we need to think about a kind of interlocking system rather than reusing the same method. And next, before we move onward, sorry. Okay. So we started looking into vernacular solutions to allow this kind of arid region architecture, focusing on Fez el Valley in Morocco. And we extracted several spatial parameters. First of all, the city is built in such a section that leaves the outer climate outside and allows for passive cooling on the inside. That is done by section and also by plan revolving in each, with each block revolving a central courtyard. Secondly, the utilization of passive cooling through the section of the streets, so allowing basically wind to go through the mass and through the streets. Within the unit itself, the housing unit, its outer rim, its outer walls are very thick, allowing very little thermal mass through. Again, revolving on courtyard, and introducing a kind of gradients of openings from the outer rim to the inner, becoming porous towards the courtyard. The main spaces revolve the courtyard, and also there's a gradient of use. During day or during winter, the bottom floor and mainly closer to courtyard, and the outer part of the structure is, for storage, and also serves as protector from the heat. Finally, what we're trying to do is to combine the two, to take those environmental parameters and have them implemented and affect every single part of our design, from the component to the region, to the settlement itself.
Okay, so starting with typical terrain sections and plans that we can find in desert regions, we look at the wadi. The wadi means in Arabic the river. And a typical section would constitute rocky mountains enveloping about a thickness of 2 meters of clay sand, where the hint of the flooding happens scarcely in the winter. We categorize in this section some levels of construction as we imagine our robotic fabrication to happen on site. So we utilize the wadi area, which is in the middle of the two mountains, as it has a clay sand 2 meter thick section of soil. We utilize this place in order to cast our components, and we adapt our fabrication process from the metal casting process, as they use clay sand for the molds in order to cast metal inside. We adapt this into our material system, and recognizing that this is a virgin territory of extreme climate, we know that we need to build everything from scratch. So we start building first our terraces around the wadi. We do this in order to collect water and to manage flooding situations, and also to manage irrigation and rainwater management, basically. Then we move up into the main street networks that connect all our settlements from the top of the mountains to the terracing and the middle settlement sites. We have vertical streets that we need to adjust the angles for robotic fabrication, so that the robots that do the pick and place can actually climb above them. And we have horizontal streets that connect settlement to settlement. Settlement size usually in arid desert places are about 13,500 square meters per settlement cluster. This means that within this vast valley, because it's basically a huge site, we would need to develop more clusters together, so we would need to use to find a strategy of how to allocate these on the mountains. So we start by summarizing all the information from the previous case studies, and we do a form-finding strategy in our building block. We start by creating the footprint according to the vernacular case studies and the building blocks square meters. We orient our streets according to dominant and storm winds. We want to block the storm winds, and we want to allow for the dominant wind to bring airflow within the building block. Then we offset our yards in the middle of each building according to the square meters per building. We create a gradient of thickness in the walls according to vernacular architecture. This helps with thermal mass, passive cooling, and it also keeps noise outside of the buildings. Finally, we splice our buildings and we offset our buildings according to sound path. in order to create self-shading, we analyze one of the building's units, which means the actual building in the building block, and we categorize the surfaces in this building block as 3 types of deformation surfaces. One would be surfaces that need to be deformed in order to help with self-shading and airflow. The second one would be surfaces that need to be populated by some sort of bumpy component in order to increase self-shading. And the third one would be surfaces that need to have some sort of porosity in order to increase airflow. Okay, yeah, sorry, go.
Okay, so we analyzed the random shapes of components on a surface to study the radiation analysis on these surfaces. The minimum value that we achieved was the shape that is enlarged. And okay, go ahead.
This goes hand in hand with our deformed surfaces. Basically, we were looking to solve the problems of the straight roofs. In order to do so, we started looking into dome geometries. Those can assist us in several ways. First of all, changing the section of the room would increase thermal comfort. Secondly, once we're starting to talk about radiation combined with a kind of structure that works in compression, it goes hand in hand with the parameters of our material. Lastly, what we were trying to do is subdivide these domes into different zones acting in tension, compression, and responding to sun path. So zones of different radiation. In those zones of different radiation and action and tension/compression, we design different components to go hand in hand. Allow self-shading, allow passive cooling, or structural components that could hold the entire structure. I already got into it, I'm sorry. So this is an example of the different components. What we are able to do through the utilization of the grid that creates this involuted components is by changing a single parameter, we can increase the curvature of the unit, we can increase the overall dimensions of the unit, and thus affect the amount of light coming in, the amount of wind coming in. Lastly, in the bottom, we see the structural component that would aid us with reshaping our terrain and territory.
Our interlocking principle is a dry joinery system, unlike typical brick construction where mortar is used to join the terracotta bricks, which is a wet joinery system. The principles we studied include funicular structure and the study of igloos, with the locking of components in planar load forces and perpendicular to planar movement is locked by creating an angle on the perimeter of each brick. So to restrict the movement of the components, we curved the edges of the components or the faces of the components to basically to restrict the movement against the shear forces. This is how the curvatures on the sides have the sine curves, and the curvatures on the surface of the component is basically for the self-shading purpose. Okay. In this section, we examine the categories of components and their respective robotic fabrication method. For the 3 building components types, we study metal casting and adopt the principles of mold making into our own material system. In metal casting, clay sand is used as the mold material. A pattern is used to create the casting cavities. Usually 2 pieces or more need to be used in order to create a casting with a different top and bottom surface, while a series of small void tubes are designed in the mold in order to cure the hot metal. Once the molds are assembled and in place, they are called gating system. In any kind of casting, the mold cavity must be designed with a slight angle at the perimeter, so that when we pick the component, it's easier to pick it than the vertical sides. So in our case, our material solidifies very fast. And it's very viscous, more than the liquid metal. So in this case, we designed a single pattern, one pattern for the whole process of casting. And this piece, the mold, is basically used to shape the mold and then used to shape it again from the top surface, so it creates double surface from the bottom and the top. Okay.
So, in a second part of the robotic fabrication, we do a pick and place, it's the pick and place assembly part. So we start to connect all the things that we've seen up to now with how this is going to work on site. So on the component scale, we start to see that we will need a face that can actually be attached and correspond to the gripper. We pile this component into specific piles and we connect this to toolpath, and as you can see, the toolpath grows from unit to block to regional scale, in which we find the sequences of building and what needs to be done first in order for the robot to be able to go back to the component piles, get more components and build again. Angles, again, we mentioned that angles of streets need to be adapted in order for the toolpath to work, so that the robot can do it.
For our fabrication, we used the DCP system developed by the MIT team, which is a very robust robotic system that has a radial reach of more than 10 meters. Adopting this system in our fabrication process will allow us to lift and precisely position the components together.
Finally, in our immediate steps, we realized that we have covered most of the territories of our project, but we haven't yet understood exactly how many components it will take to build a house. We've finalized the dome, and we realized that we will need 6 gradients going from environmental to structural, but 6 gradients in one single dome that has one single curvature into a whole block and a whole territory might grow into an enormous number. So our first step is to realize how many types and variations, how many variations we need per component type, which will lead to an adaptation of the robotic fabrication. If we need to adapt our robotic fabrication, we have some ideas. If our component, if our pattern size remains at around 90 patterns, we think that we will be able to do this with a mechanical jig. If it grows further, we realize that we need to develop a toolpath that adopts a CNC kind of methodology. Yeah, that's it. Basically, you see our fabrication casting factory in the render. And this is as far as we've gone. Thank you. Okay, it's okay.
Thank you. Before we begin, I just want to mention that this is an EMARC-only team, so they will be submitting in 3 months' time. Irene, maybe would you like to start?
I just realized towards the end that it's EMARC because I said, we just started. Yeah. Super exciting, great presentation, very exciting topic. Interlocking is my favorite technique. I try to push it in every project I'm involved in, but it's difficult.
Yeah.
So what I would like to see next is, do something that someone, be honest with what you can do in the 3 months you have, and do something that hasn't been done before, though. You know what I mean? Like I've seen sand packed, solvents. Focus on something, maybe solar sintering of the sand, just don't go to, I would love to see that, it has been done before, so, try.
We have experiments upstairs if you want to
Super, do it in a more compact way, don't repeat what he's done before, find another angle, super exciting project, well done.
Thank you.
I think my question would be, again, and I completely agree. I think this is it's a brilliant way to look at kind of components and materials. But my question has to do with the scale of your brick. Because as soon as you bring a robot, then the human scale of the brick that is constrained by what it can carry comfortably and piece together kind of becomes irrelevant, and then you are constrained all of a sudden by this kind of robot and what it can carry and can assemble. And I would imagine that, in a way, the reason you went for brick as opposed to larger prefabricated components is because of the spatial variation that you can achieve with a brick. I'm guessing, and in a way, I think it would be kind of interesting to sort of gauge the conversation of how much kind of let's say, geometric freedom you can get at different scales. And one would imagine that there is an efficiency, inherent efficiency in larger panels, but obviously you don't want to kind of create buildings that are all exactly the same, you know, and therefore, where does the brick kind of need to stop in scale to kind of give you that flexibility? But you know, at the same time, you know, obviously make the process more efficient and kind of, you know, recognize the fact that this is not a man-made structure. This is a structure made by a machine.
This interconnects with our last point, realization of this project. And as you very successfully mentioned, we have 3 months to realize this, and we need to think of our skills. A larger component will help us out because there are things that we can do, and this is a large-scale project. So even by putting all the parameters in our presentation, they will be done. However, we don't want to compromise morphological variation. This is why we started this project. Everybody does sound. We tried sintering, we broke a machine here, and we broke it twice. We loved it, but the thing is, when you start to scale up, it doesn't work. With these components and the modular system, you try to find a balance between the small and the big. You try to find a balance between the custom-made, and we don't have a strategy yet, unfortunately. It's a very hard subject. We don't have one yet. But
if I may add,
yeah.
The one thing we've been analyzing the structures from outside in, and one thing we're missing in this process is inside out, in a sense, because we're constantly talking about how a person would feel like inside, thermal comfort. So maybe now that we're looking into thermoanalysis and just to see how wind flow affects it, this would be another parameter to inform the size of our unit, because this affects the openings and back into airflow inside the structure. So that's our basically next step.
Maybe somehow would be my comment. I also really like the presentation. I mean, it's beautiful drawings and everything quite clear, but I think there's some gaps in how do you tell the story. I mean, I don't know if the driver of you is to see what you can do with sand, see what you can do with robots laying bricks, see what you can do with interlocking, or how can you change the urban morphologies in those regions. What is the driver? I think you should somehow phrase your research question in a way that this gets clear. I mean, did you start with those interlocking bricks and then okay, maybe we can build those houses with this, or do you want to change the morphology of those houses and then came to the I think you should think about this the next month and then just tell the story in this way, then it becomes more clear for at least me. I don't know.
Thank you.
You wanted to? I think the issue of the robotics and the relationship between the robot and the piece, you are grabbing it the wrong way, I think. I think you would have to bring these bricks there, big. You would have to show big images of them, tell us how they do interlock, play a bit, and try to figure out what is it that the interlocking is doing, so that the robot then is post-designed in a way that it makes it easy. You don't want to find a robot that is so smart that it does everything you want it to do anyway, because there's no design there. It's like, yeah, the guys from MIT are very good, but we don't care about them. We want to see how the way in which you drop 2 pieces, they do whatever, so the robot is a much simpler robot that just simply lets pieces fall down and they interlock, whatever. Like, there must be a way in which your interlocking, in a way, helps the robot to be easier, more sturdy, can actually adapt to whatever geometry, you know. Like at the moment, it seems that somebody is going to sort out the pieces for you later on. And perhaps you just need to be less ambitious, just be more playful and figure out, hang on, this is the way they look, hang on, so why don't we just simply drop them from the top, or whatever it is that they have to do. I think questions like these will help you focus a bit more. Perhaps it's just doing too much, like being able to invent a new type of interlocking and then change the typology of the buildings. It may be a bit too much, so you can focus on the way in which they interlock. It seems that the best is that they produce these types of walls, which actually is what they have there, and that's about it. So, you have to focus in this type of playful way. You have to sort of like see what you've done. The images are a bit too small, so I haven't seen, this thing of the picture, like, I haven't seen it there, or perhaps it's broken because you try to interlock and it just broke. It could be, but yeah. Also, just one little thingy, if you're working in the wadis, not sure if there's sand there, or I don't know, like sand, there is sand in parts of the desert, but it's just not everywhere is full of sand. So maybe that they do things with clay there, and it's a type of a funny adobe that is done with a type of clay that is also abundant there because the clay is in the mountains and the sand is whatever, you know. But I think that's maybe less important, but the issue of the interlocking seems to be more there.
I would like to continue on the points that he mentioned. So, first of all, the presentation is really interesting, and the top and the study itself. But most of the weight went on the context and the environment, and this is more like a material study, as I understand. And there was little information about the study you did on the material itself. So first of all, like you were talking about the interlocking system, so I don't understand where is the interlocking or how does it interlock? Are these your drawings or are these a reference to someone?
This is a reference to Yellowfin.
So this is not your own proposal?
Not, but we modeled accordingly. I think the one thing we're missing, so we're going to have to invite all of you to our studio to show you our units. I'm very sorry that not here and tangibly.
Yeah. So again, like this image.
We started from that phase, later realizing that we need to increase friction and at the same time to change the location of material and the amount of sulfur put per place to go hand in hand with that friction, because again, this is sand. So if sand to sand becomes frictious, it starts dissolving. So we took from that example and move onwards to the next interlocking phase.
Where is your component? Is it here in the presentation?
It's the one with the sand render.
Can you
all those sand renders? The previous one.
Yeah, because it's too. Oh, okay. So these are your components.
Yes.
And do you have any sample that you produced with this geometry?
We also have a 1 minute video if it's possible to show. It's a 1 minute video if it's possible to show.
And did you also like look at how does this sand component behave on the edges, because it's an interlocking system, so it's.
Yes, we started with the puzzle collection, and we started with the most complex component in our topology system, which is the porosity one and the involuted one. So what you see, basically the diagram with the interlocking, happens in two different interlocking phases from an opposite angle. This is how we started doing it, and we started with the most complex one so that we can see if it works. Then we worked out the geometry and we modeled it and analyzed it and we put the structural and environmental parameters in order to actually vary the geometry for different reasons according to the structural needs. We don't want to spend a lot of time in the interlocking. We started this project because the fabrication is interesting.
Yeah.
The timeline is interesting. So we thought that a simple principle would actually help us move ahead of this phase in a sense.
Thank you.
Makes sense.
Yeah. Hi, thank you for the presentation. Just one comment, like, it's interesting how you analyze the existing structures in your site and how they work environmentally with the internal courtyard and the section of the buildings. But when you were showing how you're going to map out your urban fabric, you use the same principles. But in my opinion, you have a building material that works best in compression, right? So the dome is good, but does the dome correspond to the same urban fabric like principles? Would you draw the roads in the same way people used to draw them with the way they were building, or would you actually draw them in the way that would make use of your fabrication process, which is the topic of your research? So if you know that the robot, I think you mentioned, has a 10-meter reach, how can you put that all on the table and start designing an urban fabric that actually corresponds to both the material system and the fabrication process?
This is a very good question, and it's part of the realization of the project. We're talking about reach, we're talking about scale, and we're talking about this is actually the most important part for moving forward. one way to do this, and because we want to simplify our life, would be to actually find 3 types and 10 types of variations and try to model different geometries. A problem with modular geometries is when you have a large span, you need to bind it in order for it to stand. Floors and straight terraces don't work, cantilever systems don't work, especially with joinery systems that are brittle. So a way to actually create morphological diversity and to create a city that does not look exactly like those ancient cities would be to turn these floors into like larger spans. But we didn't want to show this yet because we don't know if this is our strategy of creating a variation in this programmatic and urban system. Because it would affect programmatic parameters as well.
We started looking into how the robotic toolpath and movement in space would later inform basically the shape of the emergent settlement. So streets that would take place are affected as if streets here were once affected by the sizes of carriages, so now robotic fabrication, which is a very weird combination between old-fashioned material, contemporary fabrication methods. So that's
Okay.
We're headed there.
Thank you. Thank you. I think it's good to reflect on the different scales, definitely, and emphasize where your, focus areas are, so that it will be kind of more legible in a way to understand what the focus or the aim of the thesis is about. But we will talk about that in the following weeks. Thank you, guys. Thanks.
Thank you.
Good afternoon. Our topic of study is agrarian urbanized deltas. I'm Kavya, this is Mihir, and that's Mo. We are MArch students, and Mo is MSc. Deltas are landforms created at the mouth of the river and have always played a crucial role in the progress of human civilization as agricultural production centers. Even today, they offer conditions conducive to economic growth and development, as a result of which there is an exponential increase in population. As per UN urbanization prospects, in 2050, 650 million people will live in deltas and coastal urban regions. The delta is required to perform as a complex adaptive system to achieve a fine balance between the ecology, delta landscape, and the urbanization. Therefore, the prime concerns that need to be addressed are the natural forces that exist and the effect of anthropogenic activities. Our domain of study is the region around Ho Chi Minh City, Vietnam, which is part of the Mekong Delta. The 25 square kilometers of area of study is located just outside the existing developed city, but lies within the boundaries of the city region and has potential for near future development. The current land use of this area is predominantly agriculture, which would provide us with the opportunity to simulate the transition of the landscape from agriculture to built and thus urban. This region typically faces 3 critical issues which are being addressed in the study. Firstly, the problem of flooding, both pluvial and fluvial, which is further heightened by the lack of open ground in urban areas, decreasing water penetration and increasing surface runoff. Secondly, drought as a result of decreasing water levels in the river, causing seawater intrusion and increasing salinity. Thirdly, land subsidence caused due to properties of the soil, groundwater extraction, and pressure of the buildings on the land. This brings us to our research question: what is the potential of an agrarian urban model integrated with a decentralized water management network to perform as an adaptive solution to mitigate the negative impact of flooding, drought, and land subsidence on a delta? Our approach to this study is mainly through computational experiments from which data is abstracted and overlaid on urban design principles to develop a bottom-up methodology for abstracting an urban fabric with the core intent of addressing the problems at hand. The abstracted and evaluated data is streamed into each design strategy as required and in a mutually compatible manner through data synchronization. A multi-layered design strategy has been adopted in the study to propose for solutions that integrate the process within the context and help construct an understanding of why the strategy, method of design, and expected outcome in each layer. The design proposal developed is thus an integration of interdependent layers, with each subsequent process taking into consideration the preceding layers and reflecting the outcomes of the same. Rationalization of the final output is done through critical analysis of the system developed and its performance.
The data is extracted through the 3 types of analyses. The topographical data is abstracted from the digital elevation model. which is divided into the cells. Each cell represents the data. This data includes the elevation difference, a slope degree, and the slope aspect. The historical data is analyzed for the flood and the land subsidence pattern. The data collected is extrapolated to achieve the future worst case scenario. Lastly, hydrological data is analyzed to abstract the drainage pattern from the DEM. And further, this is used to divide the patch into various major catchment areas. The surface runoff from each catchment is calculated through rational method to identify the primary and the secondary catchments. Now, moving towards the design strategy, the level 1 is water network. The region has two seasons, wet and dry. As depicted, during the wet season, the entire patch receives ample amount of water. But during the dry season, only the area that are near to the river receives water, and that also it's saline. So the proposed solution is to collect the water at the major catchment areas in the wet season and using it and distributing it into the dry season. Further, this would also help in lowering the flood level as it reduces the surface runoff to the river. In the system logic, the upper catchment or upper or secondary catchments are referred as a seasonal storage, while the lower or primary catchments are referred as a peak storages. These hierarchical connection is established between the two via intermediate nodes which act as a secondary storage points. The set of possible locations of these secondary storage points are identified using the factor maps. This includes the factor that facilitates the low evaporation rate, a reduction in the occurrence of subsidence, maximum collection of the water, and the ease with which the water can accumulate it. The genetic algorithm is run to pick the suitable points for the secondary storage. Thus, a network is formed through minimal spanning tree algorithm connecting all seasonal storages with the respective peak storages through peaked points. The fitness target of each individual is to achieve a dispersed, well-connected, and reasonably integrated network. It is also ensured that these points exist in the hierarchy of the heights. The outcomes are then evaluated on the basis of the maximizing the total coverage area. The resultant network is then translated into the topography. The points are connected along the line of the minimum path resistance. Physically, the point depicts the storage, water storage, while the links depicts the constructed wetland that aids in channelizing and filtration of the water. The network consists of the two states, the open states in the wet season, while the controlled state in the dry season, where the supply of the water is controlled on the basis of the demand in the secondary storage area, and thus it makes network adaptive. Moving towards the level 2, that is land use and the density mapping, we shifted towards the smaller patch of area 3.75 square kilometer for the ease of computation. The patch has a very low elevation and experiences high flooding. Therefore, currently it's only used for agriculture purpose. The land use assigned for the area must be compatible with the existing context. Therefore, a growth algorithm represented through cellular automata is used as a method to achieve the land use map, and each cells act as a relation between the context and the context and the land use. Initially, the cellular representation of the topography contains a cell with a two state, that is water and the agriculture. As the CA progresses, the agricultural cells switch into the built on the basis of certain rules and the algorithm pattern. The CA stops when the 2:1 ratio is achieved between the agriculture and the built.
Yes, and the data matched to each cell are from capital maps with preferred values to located the low-risk zones, the flatter typography, the high elevation, and the less compactable soil type, and optimize supply of the resources. The factors are synchronized while giving preferential weightage, and on intuitive grounds, higher weightages is given to proximity to storage and ecological risks. From the land use patterns at Emergent, it can be confirmed that the growth algorithm ensures connected cluster formations, which is a more realistic representation of urban growth patterns. A critical analysis of this process is that we have gone in with intuitive assumption rather than generated weightage values for the factors. Three urban density zones, low, medium, and high, are mapped out based on the cumulative ranking with the factors of flood and subsidence risks and proximity to storage. The low density is close to the flood zone and on the high subsidence risks area to reduce the impact of disasters and reduce the pressure on the topography. And the high density is near the storage to optimize the resources supply.
Moving further, layer 3 consists of the urban infrastructural network. The division of superblock zones emerges from the regions created by points on the patch which is proximate, which is closest to the particular reservoir. And these superblock acts as a catchment area for the reservoir within the superblock. Primary roads exist along the periphery of these superblocks. For the following analysis, one cluster is chosen and worked on for ease of computation and concept clarity. Within the cluster, the primary road networks are identified, which are further divided by secondary road networks that intersect with the water network to form blocks. And these blocks are then divided as sub-blocks to have a grid that offers control over the system. Just describing the secondary network. Secondary network logic is based on subdividing the superblock to achieve maximum connectivity between the primary network and the water network to help direct maximum surface runoff from urban areas towards the water network. The urban network is also intended to permit airflow through the urban fabric, and thus the secondary roads need to align along the southeast direction. With these fitness criteria, a generative algorithm is run, and the results are evaluated based on the network integration.
Next one is the layer 4. Layer 4 is the urban build. The building morphology on the configuration on the wetland reflect on the wetland local architecture, which caters to mitigating overheating and flood protection. The concept of courtyard and voids has been explored for horizontal and vertical airflow, and each subblocks are divided into 9 building cells. The buildings which are in flood area are based on the stills as an adaptive measure. A generative algorithm is run to develop urban morphologies that respond to the high population density, having maximum voids, and environmental factors which could reduce the overheating. The morphologies that emerge are evaluated minimal radiation on storage and wetlands in summer to decrease the evaporation and the maximum radiation on agricultural land in winter to increase the productivity, especially for areas within the urban fabric.
Moving to layer 5, it consists of the agricultural system, and the strategies for this is developed from a combination of land use, land subsidence, and flood map. Therefore, two main criteria that determine the type of crop that is grown is the location and the season. Perennial crops exist within and around the urban fabric as they grow through the year and should not be affected by flood, while at the same time help reduce land subsidence and require minimal resources. Seasonal crops that contribute towards intensive farming are grown in areas where water is abundantly available. Paddy is grown through the wet season, which is replaced by wheat during the dry season. Salt-tolerant species of paddy can be grown near the river during dry season when the river water is saline. The design proposal consists of an integration of the discussed layers to achieve a sustained existence of the urban fabric. The wet and dry configurations of the water network and wetlands contribute greatly to the spatial character of the urban fabric. The roads are permeable, and below these exists a system that can help direct water towards the wetlands to help accumulate surface runoff from the built areas. The combination of voids and courtyards enhanced by the overall configuration of the buildings permits for the required ventilation. The overall density gradient in buildings optimizes the demand and supply of freshwater resources. The system is analyzed on three criteria, namely workflow, spatial analysis, and performance analysis. We would like to discuss the performance analysis, which would contribute to proof of concept. In terms of flood adaptation, natural landscape or unsealed grounds are considered as agricultural land, and 10% of the rainfall on these areas is directly used for irrigation. Sealed grounds or built areas contribute to 75% of the surface runoff, which is accommodated in the water network, and therefore on evaluation of the performance of this strategy, it is observed that 86% efficiency has been achieved between surface runoff and holding capacity of the storage while considering inflow only. In case of land subsidence, a comparison between the degree of subsidence and height of the building is drawn to check if the adopted strategies have ensured compatibility between context and... Okay. Thank you. Last slide.
Start.
I think something you haven't explained, and you may have time for between the final deliverable, is how the specifics of the delta are influencing that system. Like, I'm not entirely sure where the water comes from when it floods. Is it that the sea sort of like surges and comes in and just floods everything, or is it you haven't actually explained how? And the reason I'm saying is that depending on how it does it, there are typological questions about it. For example, in the case of London, when there is flooding coming up from the Thames, there are the so-called flood cells, which are areas which are flooded if a piece of the flood defense breaks. So the entirety of London is broken down, even though you may not know it, but it is broken down into these cells. So what you try to do is to figure out whether there is enough time for the water breaching part of the wall to filling an area. That is because the flood only happens under certain circumstances. It doesn't really flood everything. So I don't know if that's the case there, if it becomes, like these images we are seeing of Irma every year, that literally everything floods, or not. So these specific things will tell you whether you need to add another layer into that cellular automata distribution. I don't think you have to change that, but it would be good to actually add another level of intelligence to the parceling system, or that layer of cellular automata, which at the moment looks that it could be in any floodable area, because you don't, I'm sure you know, but I don't, or you have not been able to explain properly how this And there may be some floodings where you just simply can't avoid because they are completely overwhelming and you avoid X, Y, like you also have to be a bit more specific there.
Typically our area is, we have fluvial and fluvial flooding occurring, and it's lowlands, so essentially the entire landscape gets flooded.
Everything?
Yes, the entire landscape gets flooded. So we're trying to control the surface runoff towards the river and allocate it at different points, so as to prevent the river flood overflowing outward. That makes sense.
Okay.
I think it's a lack of explanation.
Yeah.
Yes. Get your point.
Hi, thanks for the presentation. So, in order to approach your problem, you have run a series of analysis at different levels, right? You start with the water network, then the land use map, the build-up, road network, etc. I think it would be very helpful in your presentation to show how they all combine in one, to have one 3D of your area like this one, and after you do the first analysis, like the water network, you show it on the area. Then after you do the land use, you show how this maps with the water network. So it's understood as one single problem, because now I think it was a bit like different analysis that were run. Even though they are all on the same topic and the one follows the other one, it would be more clear to show how they connect to each other. Yeah. Yeah.
Thank you. I think what I'm incredibly curious about and kind of intrigued by the model is sort of kind of zooming in and looking at all the incidental kind of conditions that occur when the street intersects a square pixel. It intersects the water. Kind of how how does the city actually sort of work from street level, from eye level, and I think, I mean, in a way, it'd be great to have kind of a qualitative layer that sort of looks at kind of urban experience as well, and in a way, I mean, it's kind of it's a very intriguing kind of sort of form, and one would sort of look to kind of exploit its potentials as well. So, for instance, you have the ability to sort of look at views and look at density, and is there kind of also a sense of value as well? How is there kind of a, let's say, kind of a real estate proposition here where it's better to be next to the water, or it's better to be next to the land? I'm not sure, but in a sense, the richness of this kind of throws all these kind of accidental qualities, and I think that there's something there. It's almost kind of on the fringes of kind of the performance of the system, where it kind of almost sort of stops performing, but actually that's really when it becomes really, really interesting, that kind of pre-failure moment, and it would be nice to see that as well.
Considering a lot of critical analysis, we looked at spatial qualitative analysis, which I think would cater to the idea that you proposed with views and evaluating those aspects.
I agree with most of the things that were said, but I also would like to see an explanation why you choose the tools you used. I mean, why do you think the cellular automata is a good way of designing urban fabric? Or is it more like distributing masses, but then there should be a next step of designing it? And also, now you said you wanted to use some tools to evaluate the urban space, but I think at one point we also should maybe step back and look at it, what all our algorithms did for us, if we like it or not. Because, I mean, that's... I don't know, I mean, after all you said, I can also not understand why all the houses are at the river, which brings the flood. And it's, I don't know, I mean, it's... at least if you use all these algorithms and processes, then you should show a variety of, if you weight certain things in different ways, and what's the influencing on all your parameters you analyzed. But then also say maybe your personal opinion, if you are satisfied with
I agree to last three comments, and I just want to put them together a bit. First of all, your process-wise, it's really methodological. It's really, in each step, in each computational experiment, you guys know what you are dealing with, and you explain the rules clearly. But as Axel said, this system that you developed is so solid, and it's also too integrated into your design proposal. You have this slight misconception of seeing your computational experiments as your design proposal. Maybe at the end of each step, you need to step in to see what kind of design quality you can get out of these. As also Andrei said, you'll be seeing local conditions appear between streets, water network, green spaces, and your blocks. So you need to design these conditions. You can't just keep having everything out of your computational experiments. And maybe, for example, as a first step in your MArch phase, you can start analyzing these local conditions. And actually, yeah, that's it, I think.
MArch phase. Thank you, guys.
Thank you so much. Good morning, everybody. My name is Massimiliano Battisti. I'm Master in Architecture, and today I want to show you how much I like the clay-based material systems in an African habitat. My research aims is to develop a clay-based material system in the rural Africa for a building construction. This material system has to be inspired by two different concepts, which are the low-tech fabrication and the high-tech performance, and at the same time it has to be environmental friendly. The clay material system, it will be a clay composite, where the clay it has been used as a binder, and the natural fibers are introduced in order to reinforce the material and reduce the possibility of a fragile shear break and increase at the same time the elastic module. My location is Lilongwe. Lilongwe is the capital of Malawi. That, despite it is the capital, it's a really poor region, and I could understand that on the land there are several different rural communities that can be used as a location for my research. Specifically, I have chosen one that is more close in proximity to the urban patch, and more precisely, it is close to the urban patch 50, and it rises from a green area that you can see on the top right. The climate in Malawi is a sub-Saharan climate. The wind it blows from the southwest direction with a top velocity of 14.5 to be precise meters per second, and there is a rainy season that runs from October to April. The temperatures are elevated during the latest part of the year, while the relative humidity it rises during the previous part. In order to address a problematic to discuss in my research, I started to analyze the vernacular architecture in Malawi. Vernacular architecture has been analyzed and then trying to understand which were the best advantages of this architecture and all the drawbacks. And more precisely, I found out that the most dramatic problematic in the vernacular architecture can be focused on the walling system that presents small openings that are not functional at all for the indoor ventilation. The poor ventilation is a driver for the proliferation of mortal illnesses. My research question is, can a clay composite material system be applied in Malawi in order to improve indoor natural ventilation without compromising the thermal performance of the building? The process starts from data gathering and runs to the system development itself that is planned in three different stages, from the local component to the cluster morphology and the building morphology itself, using as methods computational parametric modeling, structural tests and physical prototyping, dynamic mesh relaxation, and an evolution solver for the cluster morphology. All the data that are the outcomes, they are analyzed with the finite element methods, with the thermal analysis, CFD analysis, and solar radiation analysis. The three main case studies that I appreciated and they inspired me, they are Eladio Dieste with his Gaussian volt that taught me how to use basically the material saving weight. It's a lightweight material system this way. And I appreciated also Miguel Fisac that in the Iglesia de Santana used in this case concrete, but in a way that could exalt and enhance the aesthetic quality of the internal habitat. The third case is a 3D printed wall made by clay by the HAC in Barcelona. This wall is very interesting because associated to conflicting concepts such as the use of clay, that is a thermal performing material, and the perforation in a walling system. The experiment setup wants to define the building geometry, starting with a cluster geometry that uses the wind analysis to define its shape, and at the same time, in parallel, I developed the local component that has to be hosted on the building shape. The building is the result of a process of functional distribution strategy, morphological form finding, and the perforation pattern, obviously. The local component is the result of a casting method that uses fabric mold and a cone made by clay that works like a velocity amplificator with a Venturi effect. The texture has been analyzed and differentiated in order to get different patterns for the solar radiation on the surface and get possibilities of self-shadowing. And then on the bottom right, this the final shape that I chosen, obviously. The section of this element has been differentiated with three different diameters from the external, intermediate, and internal one with different ratios, and analyzed for the wind analysis, CFD, and for the thermal analysis. The aim is to find the correct ratio that can ensure good balance between the thermal heat gain and at the same time the ventilation in-house. The cluster morphology has been studied and developed with a genetical algorithm where the primitive is just a regular grid of boxes with the same shape, and the fitness criteria has been achieved with trying to increase the wind exposure, trying to increase the solar radiation in a specific area, and at the same time maintain in a range the distances between the buildings and the plot area altogether. The genes applied on this shape are three easy genes. I just used a movement on X, a movement on Y, and a scale not uniform effect to change the height of the buildings. The results are divided in and are scheduled with a ranking and four fitness criteria with best, worst, and the middle element, medium. The CFD analysis has been developed on all the phenotypes that are the outcomes of the GA, I developed and I drew a bounding box with a height of 30 meters. I applied a velocity of 5 meters per second and environmental pressure to ensure the work of the wind tunnel. And then I started to analyze the outcomes with two different criteria that are the distributions of the wind along a regular grid that are these with 6 quotes, in order to understand if the wind was well distributed on the surface, and at the same time the static pressure over the building to ensure that there was a good balance between positive and negative pressure for the intercrossing ventilation. The final shape is the result of an aggregation strategy that has been driven by the building proximities and the dimension of the buildings themselves. At the same time, I introduced different constraints in order to ensure that the main wind channels of the previous CFD analysis could be maintained in order to don't have change too much in my shape. And then the for-finding max relaxation has been developed. Of course, I'm not great. Okay, from the form-finding, I started to another CFD analysis in order to understand where I had to place my perforations. I merged two concepts like the static pressure, positive and negative, and the utilization of the shell. And I found out where was the best position for the perforations. The near future steps for my research that has to be finished in January, they are focusing on the building selection, according with the dimension of the building itself, the articulation of the block, and the position along the cluster tissue. Then I had to place with a panelization the local component in order to set up the CFD for the indoor analysis that will drive me till to the answer of my research question, possibly, and hopefully. And that's it.
As you can see, Max is a one-person team, and as he has stated, he's going to submit in January his MARC team project. Francis, would you like to start?
So I have a question about your CFD analysis on the component. If you go back to those slides, do you go back to the image?
The local component?
Please, yes.
Yes. 1 second, that is frozen. Okay, good.
So one slide forward, maybe. Yeah. So what sort of scale are those holes? What sort of diameter are they?
The scale of the hole right now is 12 centimeters and 6 centimeters. It's a small hole, but I would try to figure out if it's enough or not during the indoor simulation.
Right. Because I think on your model, are you doing a 2D simulation or a 3D simulation? This is just 2D, right?
Yeah.
For these ones,
this section.
You've got flow going around the top, whereas in fact it'll probably be a solid wall.
Yeah.
So you'll see a quite different sort of flow pattern through it. Possibly may not be more a sort of pressure-driven flow than I think. So you might want to just consider that, having actually a wall and see what goes through rather than just yeah. But it's a nice concept.
Thank you.
So thank you.
No, it's really nice. I really enjoyed the presentation. It's up my street, with all the environmental analysis. There is a great work done by a guy that now he's teaching at Harvard. It's called Salman Gregg. Used to work with us at Foster's. He did a lot of studies on breathing walls, tried to understand what's the right size for this little, like trickle vents almost. And he studied all the possible thermal effects, temperatures inside, outside. So I think you should have a look at the work he did and published, I think, last month. And some advice for you, because you're trying to do way too many things. Remind me again, the climate is
Sub-Saharan.
Which means it rains for a couple of months quite a lot.
Yes,
and then
it rains there.
Okay. So my advice to you is use the CFD analysis that you did on urban scale, to make sure that all the faces of the habitats are well ventilated so they can dry out when that happens. That's the form finding exercise. Make sure that enough space, not too much, because you want to make sure that you have some self-shading to ventilate well all the walls, because otherwise they will stay wet for a very, very long period of time. And my advice for these types, it has to be thermally driven, not wind driven.
Yeah.
Wind is not helping you when outside is hot. Because when the ventilation is wind driven, lots of air will try to flood in and then will increase the temperature inside the habitat. These spaces are not ventilated because they try to keep cool. So my advice is make sure you have very, very small holes, not near the ground, high up, and increase the height of the habitats. So rather than have 4 meters or 5 meters, try to do as much as you can in terms of the height of the habitable spaces, and start placing the holes from 3 meters upwards. So what you do, you create air movement on the top without affecting the zone that people are, so that stays cool. So somehow with this upper level ventilation, people will feel much happier and healthier, but you won't really affect the temperatures where, at the ground level.
Very good, thank you.
Well done again.
Thank you very much.
Yeah, again about these openings, when you have them like as a 2D, like you are doing now your CFD calculations, and when it's you can take like a sample room, like 3x3, and then also the distribution of these holes, because sometimes I have done previously, then you will have like a backflow. With the next hole, so you won't really have this wall taking all the air inside, but then it will go out before it really ventilates the interior space. And also you should look at the distribution of the air inside the space, and the age of the air, how far does it go inside. Maybe you should also look at different openings, low and up and on opposite walls, to really have this effect this proposal working. Thank you.
Thank you.
Just one question. You mentioned at the beginning that in the vernacular architecture there was a problem with the roof, the material, the structure.
Yes.
You haven't mentioned anything. Is it something you're going to look at in more detail?
Sorry, excuse me.
The roof
Yes.
of your buildings.
The roof, I try to use the shell in order to avoid this problem, because the roof has a problem of there is a problem of deforestation in Malawi.
So it's going to be.
They use a lot of wood for the roof, and I try to avoid it using the shell structure to go use.
Okay. That wasn't. It wasn't clear in your presentation. But that's fine.
I think in future presentations you have to be a bit careful in the way in which you present the results of the genetic algorithm. You just told us that you were using some genes and you were placing the houses here and there, and the genetic algorithm was doing something, and that's it. And you went to do the next slide. You didn't describe what you were actually getting. You were telling us, oh, hang on, I've realized that these algorithms tend to fabricate blah, 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 or tend to, some logic may emerge out of the exercise. So actually it's a form finding. You actually find something. And you just glanced over that, and you didn't reflect on
what finding you mean? Huh?
Yeah, at least in plan, you didn't tell us, oh, it's creating some form of courtyards, it's creating alignments east-west, or it seems that blah, blah. No, there is no conclusion, and we wouldn't be able to judge, oh yeah, that's the right one, right? And you should be able to have learned something out of it. I'm sure you have, but the way you presented it, it was just like, okay, next.
Thank you very much.
Okay.
It was a nice presentation. Most comments I would have gone in the same direction. I would make this CFD simulations thermal driven and not wind driven, but also again with this shell structures. I would like to see a little bit more argumentation for why the shell structure is the answer in this region for all those problems. Because okay, the roof with clay buildings might be an issue, but shell structures bring a lot of architectural issues as well. So how would you address then, how would you separate the shell in more than one floor, for example? Then you don't have vertical walls anymore, so in all your holes there would rain come inside the building. So, I mean, then I like these experiments, but as soon as in the shell, the geometry of this will change completely.
Yeah.
Oh, sorry.
So I think just the work you've done is very impressive, considering you're by yourself. And I think there are many directions, obviously, from various comments, how you take this forward. And one question for me is that, is there sort of an economy of means? Are there a number of bricks per person, for instance? Is there a site constraint? This settlement potentially cannot expand indefinitely. It's bound by something. And also, I think it's interesting to sort of look at the question of, Irene's comments just kind of, the fact that it needs to be very tall, for instance, could be kind of quite an intriguing kind of constraint as well. And I wonder how that would also translate into kind of ideas of comfort when you're inside. So for instance, at the moment, the idea obviously is to kind of inject fresh air and allow it to move freely inside, but at a certain point, perhaps it gets to be too breezy inside, it gets to be too much, and also certain activities, need to be closer to areas of ventilation, other perhaps need to be further away. And so in a way, I almost sort of wonder whether kind of a fruitful way forward is to actually shrink down to kind of one settlement and really kind of explore it more, because at the moment there's a lot of variation in the form of the overall kind of the cluster of different shells to form kind of hypershells, and I think that's perhaps where it becomes too complex of a problem to deal, especially because you're by yourself, and so looking at kind of restricting the problem to, for instance, a family dwelling. That's fairly predictable in terms of scale, although potentially unpredictable in terms of form, could be quite exciting to a problem to solve.
Good afternoon. I'm Matuna. This is Helen. We are an EMARC team. So we are looking at resource-driven fabrication in the Arctic. Our aim is to utilize resources that will potentially be available in the Arctic in abundance due to global warming to create a fabrication system to house the predicted population influx. Now, population influx is due to two reasons within the Arctic. One is the local population, which has begun to move away from coastlines because of flooding and erosion, and the second is global population, which is now starting to move towards the Arctic due to milder climates. So in this diagram, we can see the areas marked in red are actually areas with declining population, and areas marked in blue are areas of increasing population. So when it comes to current construction within the Arctic, most of the houses are actually prefab construction, which are either made with plastic or aluminium, which is not at all suitable for our site. So the two main challenges that we're looking to overcome is the logistics of materials being outsourced to our site, and the second being manual labor. Because everything is constructed manually, there's a very limited period of construction, which is only the summer period. So in terms of the landscape within the Arctic, with the onset of global warming, an interesting phenomenon is actually the thermokarst drained lake basins that are beginning to form. So because of an increase in temperature, the water within the permafrost has actually begun to thaw, and the water collects to form these lakes. Now what's actually more interesting is that once the temperature increases further, the water within the permafrost actually drains away, which leads a high amount of peat and clay. So we are choosing to use peat as a material of construction. So after doing our preliminary tests, we actually found that peat works best structurally when it is compacted. We have also added a binder, which is xanthan gum, which combines with the free water molecules in the peat itself. And we also did an experiment in relation to the freezing and thawing, and found that once peat is frozen, it actually expands by 5 to 7%. In terms of our site, we have selected a site within Alaska in the Seward Peninsula, and our temperature range actually ranges from -40 degrees to 15 degrees, with only 4 months in the year being positive temperature. Also sun radiation, we have a number of months that don't have any sunlight at all, and the months in the summer that do have sunlight have a very low amount of sunlight. Also, our maximum wind velocity is 15 meters per second. So our architectural proposal is to create a housing unit, which also integrates automation. So because of this, we have various design constraints. One being it has to be a compression structure because our material works on in compression. The second is that it must be insulating because of the hostile weather conditions. The third is our robotic reach has to be taken account because we are using automation. So to start off our experiments, we actually started with a dome, and while there are various precedents of a dome structure in the Arctic, our aim is to optimize and contextualize our dome to our site. In terms of the robot morphospace in the micro scale, while we are aiming to use the KUKA KR30 for our tests over here, because of our negative temperatures, the robot proposed on site is actually the Arctic Quantec, which can work up to -45 degrees. So our maximum reach of our robot is 3.2 meters. It has a total payload of 240 kgs and it has 4 axes. So to increase our robotic reach, we have actually proposed a rail system for our robot to increase its morphospace in the horizontal axis. We've also proposed a vertical scissor lift to increase the vertical movement to up to 6 meters.
And also, the robot has a different loading capacity in comparison to the human labor. So basically, the volume of the brick can be increased almost twice, which gives us a different scale and probably different resolution of our dome.
In terms of the robot morphospace in the meso scale, we did look at having stationary robots versus movable robots, but we found that having stationary robots would lead to having either inaccessible space. If the spaces were overlapped, then the workspace is completely reduced. And also having multiple stationary robots didn't make sense for us because our settlement scale is quite large. So we looked at having movable robots. So while we can limit the amount of robots used, because of the rail system, the morphospace increases drastically. In terms of a construction logic, we have 2 different stages. One is the compacting stage, and the second is the assembly stage. So our first stage actually needs to take place within the summer months. It includes the harvesting of the peat, and then we need the peat to thaw so that the free molecules come out and is able to bind with the xanthan within the peat. We then have to layer it and then dry it on a mesh because in preliminary experiments we found that drying our peat on a flat surface actually causes it to start to bend because the top surface actually dries faster than the bottom surface. So this would take place in the summer months when we do have availability of some sunlight. The second stage, which is the assembly, will take place in the winter months when our ground the terrain is slightly harder, and it would include cutting the modules, laying the robotic rails, and then assembly. In terms of functional distribution within our unit itself, because we are building a complete housing settlement, we looked at having common spaces, domestic spaces, storage spaces, and sleeping spaces. And we actually defined their positions based on various parameters, one being height, one being degree of privacy, exposure to solar radiation, exposure to wind, and also natural light that's required. So what we have defined is basically the habitable spaces, which is the common space and the sleeping space, move towards the back and has a increased height. So that area actually acts as a heat sink and contains most of the heat. And we have placed the storage area towards the front so that the wind would hit that area, but it's not really habitable, so it's okay. Also, we have our houses are from 1 unit to up to 6 units because from what we've studied in contemporary and in older Arctic construction, that they actually have units of single families and also multi-families to up to 6 families.
Our main design driver, as we decided, was the robotic toolpath. So we aimed not to use the robotic toolpath as the instrument to build our shapes, but actually integrate it into design process on a different levels. So on a macro scale, it's the point that we actually need to place our components from the outside because it's compression-based structure. And also the constraint is the robotic reach. On a micro scale, it's the amount of axes in the robot and the actual toolpath which will be created. So on a mesoscale, we started with the placing of the robotic rail from the outside of the dome in such a way so all the points are accessible for the robot. So our limit of the height due to robotic reach and the scissor system is up to 6 meters, and the limit for the radius of the dome is up to 5 meters because the distance from the robotic reach is actually 3 meters. But what we realize once we place the units together, more than 3 units cause the inaccessible robotic space. So we started modifying our settlement in 2 ways. One is the rotation of the lateral units in this aggregation system, and another one is just the movement, so the robot can actually reach all the points in the component. And within the settlement pattern, we selected 3 criteria we wanted to tackle. One is the wind exposure minimization, another one is solar exposure maximization, and also the robotic toolpath minimization in length. So we tried 3 different types of aggregation. One is completed compacted in units from 2 to 6 modules in each. Another one is completely detached, and the third one is the combination of first 2. And what we realized is the combined settlement is the best option because it's the optimum solution. It's the compromise in wind exposure and sun exposure. Also, it gives us more architectural variations within the settlement. Running the structural analysis for the detached housing unit and compound housing unit, we understood that in compound unit we have the utilization going up to 7% and the displacement going up to 1.5 millimeters, which can mean that we possibly need additional support in places where the domes are intersecting or where they are meeting together. And running the insulation analysis, in the first place with a uniform thickness, we understood that there is the huge heat loss in the transitional space between 2 domes and also near the base of the unit. So we added the thick base in order to prevent the heat loss, and also we added additional thickness into the areas which were required, such as this entrance space, and also the space in between the 2 domes, the transitional space.
In terms of our construction process within our settlement, so we started out with our terrain selection, which would eliminate areas with high angles to prevent solifluction, which is when our ground starts to shift gradually. So we select our terrain and then we move to the peat harvesting stage. After that, we define our toolpath sequence and then begin our structural assembly. Also, to compare it with other construction systems, we compared it to manual labor, and we also compared it to various other projects that uses robotic construction, and we found that our system actually works at around double to triple the rate of manual labor and is pretty similar to other research projects. So now that we have defined our macro scale toolpath, our intention is to move to a more micro scale and define that completely. So we'd first have to define our panelization system, how we place the materials to be cut, and we also need to define our joinery detail because our joinery does need some degree of tolerance within it. We also need to define our microscale toolpath, and because we're looking at a predicted settlement development, we also have to predict the growth of our settlement. Yeah, this is the stage where we are at the moment. Yeah. Yeah.
I forgot about the cutting it down.
Antiope, would you like to start?
Thank you for the presentation. one thing that it was very clear and everything. Yes. A thing that I would like to see is that I like how you combine the spatial, like the environmental performances with the use, and you said that I want to use like the sleeping units.
Yeah.
But what I was missing at that stage is you suddenly move to a unit that has 2 different vaults of 2 different heights, and you start talking of how they perform differently. I believe you, but the thing is that you need to prove how they work differently. Okay. Do they need to, I don't know, have a height difference of a specific scales in order to have 2 different environmental performances within the same unit? What's the maximum height you can reach? Right. I mean, you have the scissor lift with your robot, but you need to prove that the maximum height that we can build, for example, is 6 or 10 meters or 3 meters. Okay. And then in order to get the difference inside our unit to divide, let's say, the sleeping space from the everyday activities, we need to have a height difference of this level between the 2 spaces. Yeah.
Very nice presentation. I would like to follow on the previous comment that if you've done the analysis to understand the conditions we're working with in terms of, like the climate, but also the internal conditions that you will create within the dome, you will understand that the heat goes up.
Yes.
So when you increase the height in the dome, all the warm air will rise and be accumulated at the top, which means that gives you a hint of where people should be in terms of the splitting. Like you need to, use the height, but also, have accommodation up there. So at the low level, I think you should just store things, because you're always gonna be cold. Higher up is where people should live, living spaces and all the habitable spaces. Another thing I'm looking at your diagrams here is like when you harvest your material, you create a hole. What is it that is created? Is it?
So we're harvesting our material from the drain lake basins, which can't be habitable in any case. So we harvest from this area, and what we've studied is once you harvest peat from these lake basins, it actually leads to permafrost aggradation, which is the buildup of permafrost, which is something that we'd like to keep. So we aren't building in this area at all, we're just building next to it.
Oh, which is what I'm saying is that, the moment you harvest the material, you create a hole, you could use it to build on top, otherwise you're doubling up the effort. Another thing is, I understand the robotic constraints that they cannot allow you to build in compact shapes, but compact shape is what is needed in that part of the world, So somehow you have to find a clever way of fixing a problem you have created, which I understand, but you have to be quite creative in bringing these components close to each other. The closer they get, the less they have to work. So, again, well done.
So I think it's really interesting to sort of see this material, and a question for me is to sort of say, well, how does this material perform and behave differently than other types of clay, and what potentials does it unlock? I'm assuming that you're not using formwork at all when you're building this, and one kind of one moment that I found intriguing in the project is how do you get a shell so thin to work when obviously you have to distribute the load in such a way where it's robust enough to stay upright in a partial state of completion. And I would like to know a little bit more about that, because at the moment it's very nice to see the bricks here, but it's quite difficult to understand how they link together, how they work, and what the real dimension is, what the real thickness is. The other comment has to do with the fact that you mentioned at the very beginning that these are larger bricks, and because they're tailored for robots. And it'd be nice to see how the brick dries when it's that large. Does it ever crack, for instance, or how at which point do you start to sort of kind of optimize also for weight? So, for instance, maybe the whole thing is not fully made out of peat, but maybe there's a void space inside as well to make it perhaps a bit lighter or more economic in other ways.
Again, nice presentation. But I would have some comments about this robotic toolpath as design driver. I disagree with this a little bit, that I would not I cannot see the reason why the toolpath of a machine should drive the way you design those shells, and I also don't believe that's your real design driver. And the next comment to this is that I would also start with this question which just came: how do you join your bricks, because that will limit and also again your robotic reach. So all the diagrams here showed, they don't say anything when we don't know how your components are joined at the end. And then also with what Antiope commented before, now you say you have the scissor lift and you can reach 6 meters, but by a larger scissor lift and you can reach 20 meters. So why is this the limit? And do you need more? Or, I mean, I don't know. And also then you had a lot of robots on your site also for transporting stuff from A to B, and I think there are smarter and easier ways to move the components on site than using very expensive industrial robots. And it leads then to the thing that maybe you should distribute the tasks and define machines or develop machines which can do the tasks you want to do. Because, I mean, there's one reason why we use this cooker robots in schools, because we can do a lot different things with them. But if you want to build the settlement, I'm not sure if the industrial robot we use here in the school is the appropriate answer to build the settlement.
Yeah, I'd like to pick up on this last issue, and similar to the comment I made to the team from Sahara. I think you want to be building up the real bricks, or perhaps a small scale version of it, trying to see how they interlock and try to figure out for yourselves what is the optimized mechanism that may lead you to a different type of robot that, in a way, does something simpler, faster, or whatever it is. Because, yeah, I think the robot at the moment is not helping you, other than ensuring that the robot has to go around all the building, which is fine, but I think you have to be a bit more creative, and perhaps working with the material itself, trying to figure out how to do it, gives you clues. You have to be, in that sense, a bit more playful, because otherwise it sounds a bit too much of a sort of like methodologically driven project, which is good. You've done quite a lot of stuff, really, and perhaps the same happens in the plan. You present that. You've mentioned some bits about clustering, but I kind of already forgot. One of the jurors said that it's good if they're all together, so we should see one lump of them, or I mean, you should be critical about it, like perhaps we should see 2 lumps or 3, and you should be able to describe that and tell us that you've done a tool that helps you discuss. Because I guess there's a balance between getting the cost down and getting the hits maximized or whatever, and you have to make a bit more of a case for that.
Yeah, a question about the flammability issue, right? If peat's used as a fuel in northern climes, is there a possibility with a xanthan gum mixture moment that there would be a way to provide any fire retardation in the mixture itself? Or do you have a concern about, given that there'll be heating going on per unit, is there an issue with fire?
Basically, it's not defined yet, but we're considering the coating of the bricks due to the humidity as well. So possibly we can add something to the coating liquid or something, yeah, but we need to think about it as well.
Thank you. Thank you.
Good afternoon. We are Songji, Barbara, and Anne, and our master's thesis is titled Tectonics of Informality. The dissertation aims at using an integrated urban and architectural system to generate an alternative design solution for the kampongs in Jakarta, one that accommodates mass customization and growth whilst addressing the flood risk. The overarching ambition of the design proposal would be to develop a concurrent design methodology which relates top-down and bottom-up approaches, with particular focus on the relationship and feedbacks between urban and architectural scales. Kampongs are informal urban settlements of Jakarta, which grew alongside the city. These settlements provide the informal the workforce for the informal sector, as based on the. Just wait. Can you just switch slides? Sorry. This map based on UN Habitat depicts the distribution of light, medium, and heavy slums. The slum-like conditions are generated due to the increased demolition of these kampongs, resulting in the evicted residents moving into others. Coupled with the worst flooding in 2013, when overlaid the information, you see a correlation between the slums or the kampongs with flood. This is common due to the boundary condition of the kampongs being the rivers, commonly. Subsequently, the flood risk is also due to land subsidence, in which different areas of the kampongs, different areas of Jakarta are subsiding at different rates. The city itself right now is constructing or rebuilding the wall to prevent flooding. Having a mean temperature of 29 to 31 Celsius and a relative humidity of 60 to 97%, these informal settlements it's important to have natural ventilation to reduce the humidity level to ensure thermal comfort. As part of our investigation into settlements, we took a field trip to Jakarta, visiting 5 kampongs. Our findings is documented in the following video.
Usually I said you will use our local transport because I will treat you like Jakarta ordinary people.
As depicted in the videos, the kampongs are latent territories with similar boundary conditions, often lacking in basic infrastructure. Our chosen site is Kampung Melayu. The vibrancy of the communal living is evident on a public street, where neighbors and extended families often share everyday responsibilities as well as job opportunities. Dotted along the public streets are warungs, kiosks, work yards, and public toilets, the distribution of which is dependent on in its relation to the kampong. Similar to the 4 other kampongs, Kampung Melayu, our site, does not have much open space due to the gradual encroachment of the public dwelling, of the private dwelling into the public domain. Warungs, as such, are traditional local shops or kiosks within the kampong. They form the center of socio-economic and social-cultural activities, at times having no clear defined boundaries between the private and public domain. We classified the existing live-work model into 6 distinct types. The top left diagram illustrates the common types of kampong house. We also documented the most common house type, which is 2 stories, as well as its corresponding growth pattern in which different spaces are incrementally added. This is contrasted by the current provision by the government for the partial rehousing of the evicted residents. In Rusunawa and Rusunami, only 18 square meters provided for each family. The rigidity of the proposal does not accommodate growth. As such, the housings usually turn into vertical slums over time. Malay house is a traditional vernacular dwelling closely linked to the cultural identity of Indonesia. These traditional architectural forms have elevated floors, pitched roof, covering areas that are created through a changing of floor levels rather than using wall partitions. Coincidentally, the vernacular dwelling accommodates future growth through an aggregation of subsequent units.
So, summarizing our domain, we are addressing 3 crucial issues throughout our study. The flood risk, the lack of urban planning, which results in a scarcity of open spaces and lack of infrastructure system, and the instability of the Rusunawa model. Yeah, I'm sorry, I didn't know the name. So our research question is, can an integrated urban and architectural system mitigate flood risk, improve living conditions, whilst generating informality through the provision of mass customization using an open building system? We follow a concurrent design process running to 2 scales. In the architectural scale, we commence with the room unit to generate the building block through a sequential unit aggregation, whereas in the urban scale, we provide the infrastructure system defined according to environmental imperatives. The 2 systems are integrated to generate the community, which is evaluated to reinform the process in a feedback loop. The results are subsequently combined with further processed with morphological abstractions from the vernacular architecture to generate the architectural proposal. So in the urban scale, we follow tabula rasa approach. Through data processing, we analyze and map 5 key environmental factors. The values are then scored and remapped according to importance, with the flood risk having the highest weight, and overlaid to create the risk, to generate the risk assessment map. This map has, coupled with the boundary condition, has been used to define different risk zones that refer to adjacencies, to block, program, etc., as depicted in the table. So the defined zones are used as a basis to firstly distribute the main open spaces throughout the site as urban nodes. An incremental position algorithm has been developed that places 6 urban nodes in the least vulnerable zones A and B. The same aggregation logic has been used to position the hydrological nodes that refer to the main infrastructure system in the high-risk zone. This system aims at the water accumulation in the 2 reservoirs formulated in the zone E, in the intermediate part of the site. Then a drainage system discharges the water towards the river, following the topography and the slope of the site. The 2 node system networks are subsequently overlaid and reassessed to generate the primary street and infrastructure network. The hydrological infrastructure is formed parallel to the street network and directs the water to the water tanks, to the formulated water tanks, to be discharged in turn to the river.
And the other scale, the architectural scale, here we start our experiment. And first we look back to our site trip and the analysis that we find out the most common house type in the compound. And then we define the 3 family types as well as their programmatic uses. And the following experiment will use the CA logic to create the aggregation process. And here, our main strategy is about the incremental placement of the programmatic uses depending on their degree of privacy. For example, the most public one, the co-urban spaces, will be placed firstly, whereas the most private one, like living, like bedroom, will be placed in the end. And here we define 4 different building blocks depending on the initial positioning of the co-urban spaces. And we find the commonality inside each building blocks. For example, you can see the C and D. They have the co-urban spaces situated at the periphery of the building blocks, and then they generate a very clear void. And we think this generation of emergent void can be used as a strategy to link architecture to urban scale. Okay, so before going to the urban scale, we again to focus on the 3 main issues here: the flooding and the lack of urban planning, which leads to low quality of living condition, and the unsuitability of the current housing. So here, 3 strategies are defined. The first one about the flooding, we use a predefined hydrological system, and we lift up the building mass by the pilotis, and then we try to create the elevated connections between the buildings. And for enhancing the living quality, we address ventilation as a way to ensure thermal comfort. Firstly, we deal with the configuration of open spaces, and then again we use the elevated mass. And as for the social aspect, we use the incremental aggregation system that we developed, and then we create a 3-dimensional urban fabric as compared to the existing more horizontally distributed one. And here is our integrated system. The experiment setup is about that. Firstly, we select 4 patches inside the medium risk zone. And then the process starts with the rectangle packing of building blocks, and inside each building blocks, we'll place the seed in the initial open space to generate buildings, emergent open space, and the connection between them. And the following experiments that we use the genetic algorithm to hit the multiple objectives. So here we have 4 fitness criteria for them, working for both environmental and social aspect. For example, the environmental one, we have to minimize ground solar exposure and to maximize the air ventilation. And for the social aspect, we want to create a privacy suitability which match the character of open spaces to their surrounding programmatic uses on the building facade. And in the end, we try to maximize the elevated connection between the urban space of the adjacent buildings. So after 100 generation run, we have we select 4 fittest individual, and all of them reach the target that we want in the beginning. For example, the plus coverage, the density, and there are a series of post analysis of them, for example, the solar exposure, and the suitability, privacy suitability, and the CFD analysis. So apparently the top right one, which is the ventilation one, works the best. And then we have the syntactical analysis to examine the connectivity and integration of the patch.
So after our post-analysis, we selected the individual with the best ventilation to move forward our design proposal. This selection is based on the because compared to the other individuals, we realized that the emergent open spaces here are arranged and combined into a more well-related and hierarchical system of main open spaces, emergent open spaces, and private ones. And environmental comfort has higher potential for to be retained even after the future growth. Referring to the materiality of the sorry. Yeah, that was the individual. And referring to the materiality of the traditional Malay house, we established the first attempt of materializing the diagrammatic voxels into architectural elements. Namely, we abstract the post and beam circular system, the fluctuated floors which benefits ventilation, the different degree of porosity in the wall panels, and the inclined roof. As for our contemporary design approach, we integrate the shared roof that unifies the fabricated architecture volumes and the shared core open spaces inside the building blocks.
Overall, a non-linear concurrent design methodology that implements a top-down and bottom-up approach leads to an integrated system which relates urban and architectural scales. In the proposal, the emergent ground-level open space are embodied with different hierarchies and characters, degrees of privacy, which can accommodate diverse urban activities and improve the living conditions by ensuring the thermal comfort via and ventilation. The bottom-up approach incorporates the informality, abstracted into mass customization principles and the live-work model. The communities can address flood issue by the elevated building blocks as well as connections on the different levels. The existing horizontal distributed urban tissue is thus transformed into a three-dimensional one that includes open space as well as connections. Further to this, we will look into how the architectural form can be further climatically optimized through the development of the kit of parts, thus enabling an adaptive change based on user needs. We will also look into incorporating the construction sequence in the integrated system. We would define the limitation of future growth as well as the differentiation between house types and growth between the zones, strengthening the overall concurrent design methodology and sound relationships and feedbacks between urban and architectural scales. Yes.
Andrei, would you like to?
Sure. So I think it's great that you've kind of drilled down into your project at this level of detail, and you've looked at a section, and you've also sort of simulated how your sort of urban condition would work in different environments and different stages of flooding or drought. I think one thing that's interesting, and you showed in the video at the very, very beginning, is that every single sliver of available space is utilized one way or another. So the sidewalk is an impromptu marketplace. The living room is also an office and storage and so on. And I think that there is a reality here that maybe is not yet reflected in your project, which feels very, very generous with the amount of open space, and also make some decisions about how that open space is distributed in relation to streets and the blocks. So at the moment, your open space occurs near the streets, at an area where one would expect it to be the most utilized, given how your precedent sort of functions. And I wonder whether there is a way to sort of invert that model to sort of say that again, as you've determined, that there is a need for open space, but that space is perhaps removed from the street, and perhaps also works with your kind of areas of privacy and so on. So I think it's the distribution of the urban void, as you've described it, that perhaps is worth scrutinizing again. The other question has to do with the relationship of the street with essentially a building mass that is perpetually lifted up on pilotis, and what does that undercroft look like when it's not flooded? And I would have thought that perhaps that that space will be utilized somehow. People will find a way to kind of colonize that space productively, and perhaps your design should sort of anticipate that condition as well.
Do you want to go back to the section? I think with regards to the distribution of core open space, we begin by that's our seed. The core open space is where the building is generated, in which each incremental unit builds around it. But We only simulated the current density of the site. We would like to simulate future growth in which it will be increasingly more and more compact, but with the core open space itself allowing for this limiting that growth, moderating it somehow.
As for the ground level configuration, what we thought is that the outside is flooding all the time. So it is very difficult to use this space. We have to find a way to change, to transform this kind of street vibrancy into a system that will be able to adapt to this kind of environmental issues. And that's why we think that this kind of open spaces in multiple levels that incorporate wine rooms and this kind of street life into in courtyards that are moved in multiple levels. And as you can see, I'm not sure if it's very seen in the section, but maybe, yeah, this is this kind of spaces that are multi-level connected and create this kind of community inside the building block. It is how we try to address the ground level. I mean, yes, but this is what we're trying to say as a three-dimensional network or street network. So this starts becoming, and with connections, we hope that it will come, yes, in a three-dimensional.
I really liked the movie when you started because it was so helpful for us to, just to go into the space and feel. We've done something similar a while back in the office, like try to understand informal settlements and propose design solutions. And the first time we went to propose a design solution based on what should be the modern way of living, and we failed big time because we failed to understand what people need in order to move somewhere else from what they have. Because you think it's obvious, if you give them a better apartment with sanitary and everything, they will move there if they have a choice. And actually, many settlements like that in various parts of the world failed. The reason it failed is because proximity to the street is for them prosperity. So the streets are very, very important for them, for all ages. For young people, because they want to play, for older people, because this is where they trade. And also, not only the open space is the mobility network. So they trade, they sell, and they want vehicles to move around. And also older people, they want to be where the action is. Otherwise, they feel isolated. So then we felt that if we don't reinvent the street, the settlements will fail. And it's not easy because you have to design a street that is modern, that has enough space, but also try to accommodate all the flood issues that you mentioned. But lifting people up and open spaces up, it makes sense, but it's not what people need. So I would like you to consider, maybe on the next phase is how you can rethink the street. The street is everything you have.
We
and
would
how
argue that is exactly what the people need, because we did informal interviews as well when we went to site, and when we asked them what they would prefer, why the current low-cost housing doesn't work, is because all the warungs and all the kiosks, everything is provided on the ground level, when it floods, nothing works. And whereas every single house unit at the top of the building block does not have that space for them to socialize, for them to function. As such, we didn't want to produce just a typical housing block, but incorporate different provisions of warungs and open spaces throughout the entire building. I think the key thing that we want to put forward is that the low-cost housing doesn't work also because they ignored the community scale. Whereas in our target, each building block is a community in which certain spaces are shared, and how they link between one another. Because when it floods, they usually move them to a mosque or move them to a public school on a higher terrain, and the activities and everything, their livelihood, everything, if it's on the ground level, it's affected. That's why we didn't, we thought that it makes sense, since in their local vernacular housing as well, it's already lifted up. They have that kind of tradition. That's how we thought it was appropriate.
Absolutely, I fully understand they do it because they don't have a way of designing the street, because the street is there and it's not owned by them. So they try to solve the problem in their plot. They try to lift things up. But if you could redesign the street, like almost like a covered river that you can be on top, but there is the water can actually drain down, and then like channels moved away. That could be a solution. So then you don't change totally what they expect to have. And also what I noticed here is that what is very nice about what happens in the plots is that they have infinite flexibility to change the space around. They change it over monthly, move functions around. And when you provide a modular system like that, actually there is a risk that you might limit the flexibility of a family increasing in size or decreasing and all that. So, I would like you to also think which system will allow this infinite flexibility they used to have.
I completely agree with this. I mean, I think it's really nice work, but I think there came some questions that you use this genetic algorithm and you had these generations of settlements, and then you're going there and tell those people that they have to build it like this. I don't think that will work ever. I think really that address those issues, like do something with the street that those vulnerability get reduced, and then maybe provide from all your experiments and optimization process you did, try to extract some rules to give them how they should build or how they could build. But that needs to be flexible enough that your system still works if they don't follow those rules. Because I think in those scenarios that might happen or will happen, that if they need more space, they build more space. And then your system should still work, or then even you can think this in one step further, that your whole computational system should adapt to this and change the rules. Okay, now that would be the optimum, but if they do something different, how would your system react to this?
You may actually gain from adding a next level of complexity by trying to understand how some of the social relationships work there already, like in certain parts of the world. Housing gets stacked and gets grown out of the same family building up the house of the kids or whatever it is on top of it. In other areas, it's the women that actually do blah, 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 and in a way NGOs are already working with them in order to, so there's perhaps it works by families coming from the same village or something, right? But in a way you want to understand how things work there a bit more in order to propose that level of, in a way, binding that at the moment is unspecific. It just seems that it's slammed anywhere. And I'm sure I think one of you is from there, or at least gets a bit more, can actually definitely know about this and research it.
Would you like to do some concluding remarks? Okay.
And thank you for the presentation. And when you do, following up to the comment that Axel made, what I think you need to add up to the guidelines is, where is this area in your actual site? Because you made a nice analysis in the urban scale in the beginning of the risk assessment map. So is this an area next to one of the main open yards? Is this an area next to a water tank? And how would those guidelines change depending on where they are on the site? Because if you take a patch of your area who's, intersected by a main road, then the whole optimization process would change if you would take one that has the main road as a boundary. And I think it would be interesting to see what sort of changes you would get in the urban patch depending on where you run the optimization on that network and how you divide the areas.
Good afternoon. Sorry about the sound problem. We are Carolina and myself, Maria, we are MR, and Eleana and Maria Cristina are MSc, and we are going to present the MSc dissertation, Urban Glitch. Participatory design is a design method which involves stakeholders in all design process. Through experiences that are meaningful and productive, in order to achieve a design that better suits their needs. In the fields of architecture, the most conventional participatory design tools, as we can see, are pre- and post-design stages, such as consultation or public surveys. What we are proposing in this work is to develop a new participatory tool so that the user or the stakeholder can get involved in deeper layers of the design through the use of this new participatory tool that we are proposing, which is it's a combination of virtual reality and serious games. So immersive technologies have the power to make the user live more realistic experiences. All this within a game environment make their motivation higher to engage in more serious activities, such as the process that we are proposing. The combination of these fields will produce this design tool that we are proposing, and we will use it to enhance residual or liminal, called unused public spaces in the city of London, which is a high-dense city, and where you can see the darkest areas is where more unused public spaces are found. So our methodology is divided in 3 blocks. The first one for the development of the VR platform. This will include the representation, a realistic representation of the place where the user is going to play this design game. So for this, we have used photogrammetry, reality representation software, and a game engine. Secondly, to inform the game that we are going to develop, we propose data collection through questionnaire. And finally, to understand the results given by the game, we have used different data analysis, such as density maps.
For our initial experiment, we aim to create a realistic site representation. For this, we use photogrammetry. And after having the 3D digital model, we develop the VR platform. In this, we test the user navigation, the morphology of the model, how this is going to be inserted, and how this is going to be controlled. Finally, we test the game with people in studio to understand the user interaction, how immersed they felt into the game, how they managed the control, and their thoughts about the technical aspect of the game. Finally, we analyze the spatial configuration that they made for our further investigation and for next experiments. In the design process of photogrammetry, our first size was a medium size one. We take around 600 photographs, and then we did them so they have the same language in terms of brightness and coloring. Then we import this into the software, and this first gives us a 3D class of points, then a texture 3D class of points, a raw mesh, and finally a texture mesh. Although the resulting textures are high quality, the mesh itself requires a high amount of refinement to be cleaned up and to reduce the sci-fi. Well, the gaming set, we test the module, the navigation, and how to save the results. In the navigation, the user can only walk forward in the experiment, and the model can be generated by pressing the button. They can neither move them, they can lock them in place, or they can delete them completely. we got around 15 results. Some of the users found the time to really think about the site and recreate something that really can enhance the place. Others just see this as a game and just trigger the insert button like that. But regarding where is something useful for the site or not. So we can conclude that for this first experiment, we were able to create a realistic site representation for a virtual reality experience that is high level of detail and is time efficient. About the game, the user preferred to use the joystick as a way of navigation rather than any other button. The model generation was working well because this model generation was related with the user field of vision, so everywhere where the user looks, a cube is gonna fall in place. We also find that it's very important to give the user a lot of information about the game and also the site. Those are things that we're lacking, and also a more intuitive button assignment for the user to be feel more comfortable in the platform.
So based on the discoveries that we made at the previous stage, we conducted a new series of experiments that focused not only on the improvement of several technical features, but also in the establishment of a new collective design method. The aim of this experiment was to create a dynamic field of information, not only between the users who communicated through the virtual reality platform, but also between the user and the architect, where the user communicates his design idea through proposing it. So the process included a thorough site research that was followed by a survey so that we can better understand the deficiencies of the site. Later we developed an application, and in the end we got the feedback of the user so that we know how to further develop it. After investigating the unused public spaces in London, we were focused on New Era Estate, which is located in Hoxton, and it's a block that houses approximately 350 people. In 2014, the block was acquired by developers, and the residents were about to be evicted from their houses. But eventually, they managed not to do it by protesting, and that proves that they are a pretty closed and strong community, which is an asset for our aim, as we want them to be more invested in the redesign process of the public space. What drew our attention was that although it's such a close community, the residents wouldn't engage in the public space due to lack of activities and lack of facilities. So, aiming to gain a deeper understanding about the deficiencies of the site, we conducted a survey where mainly the residents, but also people who daily interact with this public space, expressed their opinion about certain major issues. The most important deficiency was the lack of activities, and most people refer to lack of greenery, sitting areas, balconies, sport facilities, and playgrounds, which we classified in 4 categories, which is greenery, street furniture, building additions, and a customized one, so that we can develop our application.
The computational infrastructure based on which our game is developed relies on the existence of an underlying 3D grid, 50 by 50 by 50 centimeters. Every time a player places a module somewhere on the site, the closest point on the grid gets a value of 1, which results in at the end in a value 3D grid. And this helped us achieve 2 significant aspects. The first one was that it gives us a significant advantage on speed during runtime to perform several calculations such as the module insertion, some shading calculations, and seating area calculations that would otherwise require significant computational force and would cause the game to lag. And additionally, the value grid, together with Martin Cube's algorithm helped us provide volumetric isosurfaces that represented regions of preference of program is what we call program hotspots.
So our proposal, the game, is built in 3 different levels. Firstly, we have included a narrative where we show the user how to play the game, because it's a single player game, through a series of simple instructions and demonstrations. Secondly, we jump to the category scene, where they select among building additions, furniture, greenery, and a free category. And eventually, we jump into the game stage. In this one, the user has to build with using cubes. We wanted them to be simple geometries so that they don't feel very biased with more complex ones. So in this game, he's able to create cubes, to place them either starting from the ground or joining next to another existing cube. He's also capable of swapping categories, and eventually there are a series of previews which are very important for us because it's where all the participatory features rely on. For example, we have a set of live information floating next to their eye, and in this one they can feel aware of what they are building. For example, we have a number of cubes that they are using, the shadowing, the sitting areas that they can create. Then they can also see collective comments and most used locations by other users. So now we can see here a demonstration of the workshop that we took in the new era state. Starting with the narrative, the user can log in so that we can get their details. These are simple instructions regarding the place. And then in the category selection, we tell them how can they pick them up and what can they build based on them. And eventually in the playtime, you can see here the most popular location highlighted in the category color. They can change categories. They can pick up a geometry that they have created to insert a comment. Furthermore, they can see others' comments in the geometries. They can also highlight the seating area. And eventually, depending on the position they are selecting, the most used flow of movement are altered. So in this one, we can see the number of solutions that we achieved. About 60 people get to play, and some of them decided to play in 4 categories, or we just picked one. But we can see that they are widespread in the area. So from this point, we want to highlight some results and conclusions. From this workshop, we received several comments regarding game dynamics, regarding model selection and site representation. It's to highlight the impact of such a realistic environment with a simple geometry. It was kind of abrupt for them, but we will treat this in the further steps. Regarding user engagement, we can say that the nature of this academic project versus a real intervention makes the user lower their motivation to engage. So maybe we can think of ways of enhancing the game, making it more gamey. I like the goal. And finally, as you could see in the previous scene, the solutions are widespread and they don't really achieve much convergence, or at least the one that we were expecting. This could be given by the size of the place that we were proposing. So these are issues that we are trying to develop, to further develop in next steps.
Moving on to the part of utilizing the user-derived data into a design proposal, we acknowledge the fact that in every design process, the architect, given the resources he has, is required to make a personal choice that reflects his personal language on how he's going to approach a specific project. So in our case, the resources were the data that we got from the users, and we were faced with two choices. One was to take the data and provide a proposal ourselves, declaring the risk of ending up somehow saying that this is the only way you can use our tool, or we could release the data to a series of architects and exploring multiple interpretations of what this data could be used for as a design. So we decided to release the data to other architects, and for that we created a design invitation, and we released a design brief, several special data, and a visualization up for the architects to overlap with. So we shared the brief through social media and Facebook. Here you can see how it was structured. We gave them a specific amount of days, around 5 days, to work with them, and we got some early results. In terms of the data that we released to the architects, we divided them into categories. The first category is the raw data, which is basically data extracted straight from the game. So it's the individual designs of the users and the hotspots that we talked about earlier. And the second category includes some process data, which are derived from a series of preliminary analyses we conducted in order to make the data more readable and usable to architects that were not involved from the beginning. So we created a more generalized ISO surfaces, some horizontal heat maps in several heights, and some group comments. And we have created an application, visualization application, that aims to help the to help the architects look for patterns in the solutions and overlap data in order to provide their design. So this application has 3 types of menus. One is to the program that they want to use to see data for, one is the kind of data that they want to see, and one is a specific one, a special one referring to the hotspots that we will see later. So in these states, the architect can slide through the individual solutions. He has selected all categories, but he can select whatever he wants. Then the next one, we can see that you can select a category and see its evolution throughout the game, like a growth pattern. Then you can either visualize all the proposals from one category, so either all together or separately. Then is the program hotspots with their own menu indicating the times these locations have been used. So you see the more condensed one is the ones that were actually used more than one time. And then moving to the process data, we have the ISO surfaces, which are a more generalized representation of preference in regions. And the heat maps are slices on the ISO surfaces that indicate preference not only in the boundary curve, but also in areas. So there are locations that were more preferred. Yes, and then we have provided the categories and comments that the architect can visualize in order to get a more refined idea of what the users actually asked for the categories we proposed.
So after announcing the design invitation, we received several design proposals from architects, mainly in our age group, 25 to 30, and we decided to showcase 4 of them. So, although we don't have, although our data set is not sufficient enough to draw conclusions, we observed a convergence in certain design proposals, which possibly occurred from design biases in our data. So, the way that people utilize data was by either creating patterns that were inspired from the individual proposals or by imitating the location as well as the morphology of the objects that were designed within the application. Another common feature was the areas of intervention. In this case, we can see interventions on the rooftops where people design socialization areas, as well as additions on the blind walls of the buildings, where they designed green vertical walls or murals. Here we can see some more detailed examples about a more detailed comparison between the provided data and the design proposals. For example, in this case, the individual solutions showed the intention of the players, which was to create connectivity between the buildings, and it is reflected in this design proposal by the creation of bridges. Here, the zoning formed the guidelines for the creation of the green areas, not only location-wise, but also in the morphology, which resembles the isosurfaces. In this case, the street furniture, which is the canopies and the seating areas, are driven by the preference of the users, which is clearly shown in the heat maps. And finally, the comments added an extra layer of information to the abstract geometries, which helped the architects to identify what the designers had in their mind. And in this case, the most common comment of this design category was the playground, which stimulated the architect to include it in his design proposal.
For our first steps of inclusions, we noticed that the participatory process can be enhanced with immersive technologies. The data collection for the users proves to be a significant asset for designers. However, the process can be improved in many ways. As we conduct experiments in the MSc stage, this is a linear process. And there is a high possibility to create a loop design process where the user can interact until the architect and the user reach a commonly agreed result. This can be more beneficial than a linear process. Another fact is the role of the architect during the game. We try to give the user sufficient information to design, like shading area, amount of seating, and people flow. However, the user remain indifferent to it. They cannot understand the purpose of this information given. So we, as architects, need to give this information in a more explanatory way, as well as the initial narrative. Everything has to be linked and understandable to a user that is not expertise in design. So in the game, we have to be able to educate the user about spatial matters and guide them to a final goal.
In terms of the game, we noticed that we have created a very strong contrast between realism and abstraction. Realism in terms of how we represent the site, because we wanted the users to feel immersed and understand the problematics. But abstraction in terms of the module we gave them to utilize, which was a very simplistic cube, and we got the comments from several users that this created some sort of confusion in what they have to do. So we are thinking of ways of, for example, introducing some sort of materiality into this module, or the ability to perform some deformation, scaling, something like this. But we are also aware that this might create further confusion, because the initial experiment that we have many choices, the users were more confused. Also, in terms of the game, we haven't fully taken advantage of the potential that the game mentality as a means of involvement, because at this stage, we lack an incentive for the players that could be introduced perhaps if there was an architect that was creating tasks for the users to solve. Finally, final comment about the VR environment is because our project is in an experimental stage. We have created a game that is a one player at a time, so the interaction between users right now has a stigmatic kind of character, meaning that the users interact with each other through the information that they leave on the field. But we would be interested to explore cases of social VR and multiplayer platforms. Thank you.
Right now? Yeah. Demonstration? Yeah. Yeah. Mark, would you like to start?
Really engaging, engrossing even project. 3 points. I wondered about the site selection. There seemed to be a lot of care with that. It seemed the right scale given the palette of options you had. It seemed to be all about interstitial space, so the Hoxton site was kind of, I think, delicately taken on with its own backstory of activism. So I would commend you for taking the care with that site. I don't think it could work generically anywhere. It would have to shift palette, shift scales, shift some other considerations. Point 2 was the moment you placed the bench cube, you had the black lines of circulation, a real-time feedback loop about the reaction to the move, and I wonder, as you progress, what other sorts of feedback you could provide. If I insert something that changes shadow lines that might hit a window of a unit, would that show up in real time? So that kind of information that you would guide placement in real time, I think, is one of the best parts of your project. Lastly, I think I want to go back to the question of gaminess. If you just take it on game terms, right, there would be the next step of sound, that there are acoustic ramifications of certain insertions, like a fountain, for example, that would change the space. And that soundtrack, and we've had moments of sound in the presentations today, but the soundtrack there, the reverberation you get in a courtyard scheme, the way maybe in the palette a tree might change the acoustics, that might be a level of gaminess that would help sustain the broader intentions of the project. But excellent work.
I agree. It's really, really nice work and well done. Especially because right now we have one student in Stuttgart. He's doing a kind of similar project about augmented reality for robotic fabrication. That goes to this comment that, I mean, he implemented basically real-time feedback for everything. He has structural analysis. He has the robot, which he, I mean, if you have enough time, you can implement whatever you want into it, basically. So, but what he never addressed, and what you really nicely addressed, is that you gave the tool to architects and let them play with it, which is, I think, really a smart move. I mean, to test it. There, I just would have one comment out of pure interest. If you would give now the same site to 20 other architects, they should design seating and shading devices if it would look similar or not. I mean, it's just, I don't know if if they would have designed it the same way or not. I mean, it's just would interest me.
Very nice presentation. One comment I have on the question that you said about how much detail do you give to the user, whether it's a cube or not, and the contrast with the detailed environment that you provide. My question would be, rather than going into more detail and giving, I don't know, materiality or a different scale, why don't you go even more abstract, and maybe the user, rather than putting 3 cubes that are of the category green and they implement that there's a tree there, maybe he just, I don't know, in your image you have these like bulbs. He just sets an area of that properties, and then in return to how much information you give, he can put, I don't know, a shading area. So he doesn't need to design the actual cubes that put the shading surface. He just says that I want the property of shading. Yeah. I think that might be interesting.
That's very interesting.
Yeah. I think you've done a terrific work. So by all means, it's really, really good. I think on the one hand, because the previous times when I've worked with participation and digital participation, we gave people more close brief, and they literally designed the hell out of it, and they told us what to do almost, literally. So, which was fantastic. So I don't know if genericness is working on your favor, because you ended up with crazy stuff that was a bit too big. I don't know how to close down genericness so that you just get something that you can grab more hold of. Perhaps there's a budget, so people cannot just fill everything with blocks, and they just have to know there's only so many benches you can put. You know, there are things that give constraints so that people think what they're doing. Perhaps just tell them more closely what they have to do, or the tools are more shape specific because you want to drive your agenda. and you don't want to end up with whatever. I don't know. I think there's a discussion on the virtues of genericness, because it gives you quite a lot, but the problems, because you end up with, well, I don't know what. And I think the next step is something you could be playing with, because it's really, I mean, you've done all the steps, the fact that you open it to others, you treat statistically design, which is a bit, or sort of like it sounds funny somehow, but I think it's really interesting that you do it. But I think you open the question of generic, and I think you have to close it.
About that, it was a conscious choice to select a generic module rather than, for example, have them catalog of trees in place or a catalog of benches, because we wanted to set them free of designing on what they know. The people that are not designers, sometimes they cannot break free of what they've already seen in the world around them. So we wanted somehow to let them do this.
But do they understand what they're doing?
It was an experimental choice, and it was on purpose. But it wasn't that it is the only way. Just we wanted to explore this.
Thank you for the presentation. I think you did really a fantastic job in presenting the project, like combining between reality and also the abstract components of the element or the methodology that you are using. And I just want to add, like, the conclusions are really good, that you continue, like, the future work that you would like to investigate or explore, and the results. I just had to say that. Thank you. Oops.
Exciting presentation, and I think you gave us a glimpse of the future. It's and you raised a lot of interesting questions, which we have also in the office. We spend lots of time debating, how to use this technology. And what I noticed is that, users, especially when you ask people what you would like to have, they will tell you exactly what they know. They don't know something that they might, like the iPhone, typical, marketing thing, like how do you know if you need an iPhone if you haven't seen it before? Questionnaires, when you ask someone, tell me what you think about something, they're often boring and tend to be misleading, because the user doesn't fully understand what you have in mind, and also it's very difficult to extract really interesting information out of their mind. So if you give them the tool, to tell me where is your favorite area. Somehow in that game they see their house, the development, in 3D, they've never seen that before, and tell them to identify where is the best spot, where is the worst spot, the more dangerous. Extract interesting data out of them in a new way, playful way, which will be exciting. And then give that data to the architects to propose solutions, which means you don't get the user to design, with abstract blocks that they're not used to, and the more detail you put, the more complex you make it. And somehow, and get the architects to design with blocks or whatever, because they spend 5-6 years, get trained how to interpret this kind of scheme design, options, this and that, understand the benefits of each, and do all the analysis, the shading, this and that, and then go back to the users and show them what you try to do with the data they provided. So somehow you close nicely the loop, because what they find very annoying, they give you all the data and they don't see anything. So with that game, somehow very quickly you give them something back. But exciting work. Thank you very, very much.
Thank you. Again, it's a fantastic project, and it's really nice to see it. I think it's an incredibly timely project as well. I mean, the idea of urban commons is something that's being discussed, and the idea of ownership over public ground that's in a way manifested through kind of an increased sense of agency from the people who actually occupy the space is terrific. I think one of the things that struck me and also I liked how you drew conclusions from everything. Your conclusions were actually really, really interesting. In kind of your next steps. I think one of the things that struck me, at the beginning, is this idea that fundamentally, in a way, this game is kind of almost sort of a kind of a consensus discovery apparatus that you basically understand. Sort of kind of areas of confluence, and actually it's something that you had a tough time trying to kind of extract. Actually, the commonality was difficult to kind of extrapolate, because in a way maybe your game was very distributed somehow, maybe it wasn't sort of focused. And even just sort of listening from the comments that were made earlier on, I think there's sort of layers in the game that maybe are adopted incrementally, and so for instance, perhaps starting from kind of a land use scenario where people sort of identify specific areas, but without necessarily sort of committing to a design conclusion, or even sort of kind of programmatic land use. I would like this to happen. You know, your site is also just only residential. It doesn't have other uses to kind of activate the ground. And also sort of following from that, I think kind of what's interesting is to sort of understand kind of a qualitative impact of the things that are being proposed. So in a way, maybe having a tree that casts a shadow is a good thing, you know, or something that kind of makes a sound is a good thing. But it doesn't, but with the caveat that this should not limit the design to that specific tree or that specific playground, or the element of surprise is still there because it's introduced by someone else, but it's introduced based on a kind of an extreme familiarity with the site that comes from this kind of data extraction exercise. But I think fundamentally it's something that I can see sort of kind of local authorities using, or kind of resident sort of kind of groups using together. You know, it's an incredibly valuable tool, and I'm sure you're right in saying this is the future, because it's very difficult otherwise to sort of occupy our cities without this kind of interface that allows us to understand what do we all want. You know, so thank you.
Well, we'd like to thank all our jurors and tutors for a very interesting morning of debates, and we'd like to obviously thank our students for all the hard work they've done. Mike, would you like to say a few words?
So I'd just like to thank our jurors for, I hope you've enjoyed the topics and the technologies we explored. We tried very hard to address important issues and to focus on what we think are near future scenarios. But thank you for your comments and your patience. So perhaps the students will join me in thanking our jurors.